Announcements. I'll put that to it. There we go. A couple of announcements to make, and we are now recording. So let's go from current slide. Now, here's the first of these. This happened this morning. They didn't send the thing until yesterday, so there's no chance to give you any advance notice. But in case you're ever on the Birmingham campuses, east or west, they had new buildings dedicated today. Ribbon cutting, official openings. The Academic Success Center. I don't know if y'all knew where Winona, it was either elementary or middle school was, right there adjacent to the Lawson campus. When they built the new Winona schools, that one was abandoned. They basically turned it over to the city, who gave it back to Lawson, or something like that, some sort of maneuvering around. And they have built this big, fancy new building there that I hear is very impressive. I haven't been inside. From the outside, it's amazing, and they say it's huge in the inside too. It looks like it. There may be 2 classrooms in the building. All of it's for administrative stuff, which I'm sure is good stuff, but they haven't built a new classroom in I don't know how long. But anyway, that was dedicated, or ribbon cut, official opening this morning. Along with that was the second residence hall. Not nearly as big as the first one, but a nice-sized building, and that's on the Birmingham East Campus. Now, the Academic Success Center is barely on the West Campus, but it's on Wilson Road, which is the boundary between the two. So it's really right close to the East Campus as well. The residence hall is on East Campus, right next door to the old residence, which is also a fairly new building. Those were both opened this morning at 10, officially. So if you want to go by there anytime, they're pretty impressive looking buildings, I think. So go by, check them out if you can. I'm sure you can get someone to give you a tour. That happened this morning. I was teaching, of course, so I didn't get to go. I haven't been in either one. I've been in the parking lot across from the residence hall while it was being worked on for the last several terms. So it seems like that should be pretty good too. Okay, second announcement, and this one's one of those good news, bad news situations. Okay? The good news is next week is spring break week. But the bad news is that means we won't be meeting next week. So sorry about that, but get over it, okay? And we will pick up then. We will meet Thursday, though. Don't get the idea that spring break begins early. It begins next week, not this week, okay? Now, so much for the overall schedule. Let's look at things a little more specific. Today, in this class, we are continuing in Chapter 2. We will do, we'll go until 3:45 in Chapter 2, and then we'll stop and go down to the same lab we've been in the last 2 times. This time we're definitely in that one because we need the long bench space to do today's lab. So we will be there 3:45 to 5:45. I don't think it'll take you 2 hours to do it. And actually what I think I'm going to recommend that we do is go down there, do the lab, just take the measurements, and then we'll come back, because in this lab there's quite a few calculations, and some of them are a little involved. So I think in order to get them down, since I can't project, and the board I used to write on, there's no board in that lab, but in the other lab, every time I've looked at it this term, there's been biology or chemistry stuff all over it, and I don't want to erase any of that. So what I think we'll do is just take the measurements, come down here, and we'll do the calculations down here. There's some you'll be able to do there, but most of them you'll do here. So I have all the equipment in the room, but I don't have it set up yet, because the only time I had to get it down there was last night around 6 o'clock. There was nobody in there. I could get it in there, but then I couldn't set it up because they had biology labs in there at various times last night and today. So it'll take me a little while, but not too long, to get set up, because everything's there. I hope I got it all. Okay, any questions? Then looking ahead, if we don't finish chapter 2 today, which we probably won't quite finish, but we'll come pretty close to it, then we will finish chapter 2 on Thursday. We'll have the third lab on Thursday for chapter 2, and that's a very short lab, so I hate that I'll be letting you go early on the day before spring break, but I guess you can handle it, can't you? Okay. It's not going to be super early, but it's going to be a relatively short lab on Thursday. And that means, unfortunately, that we'll have the test on chapter 2. Now, unless we finish, if we finish chapter 2 in the time we got today, we could have the test on Thursday. And that would be nice to get over with so we can start chapter 3 afresh on Tuesday, after spring break. But anyway, and here's...
So we can take the test?
I'm sorry?
So we can take the test?
We'll see. If we finish the chapter 2 today, we'll have the test on Thursday. Okay. This is Calvin, right? Okay. All right. And nobody else came in since we started. Okay. All right. Last time, any questions on anything about this, what we've been doing, about general schedule or anything? Okay. And by the way, I had to revise the summer schedule. I usually try to offer one of the physical sciences in the summer. I can't usually offer both because the summer term is just too short and the classes are too long. But they changed the hours on us for summer, and I couldn't even get it scheduled this summer, either physical science. So there will not be a physical science offered this summer. Sorry about that. But they'll start again in the fall. All right. Now, last time we talked about motion in one dimension, and that was horizontal motion. Today we're starting with talking about motion in one dimension, but vertical motion, okay? And you might think they are similar, and they are, but there are some major differences too. Because when you have horizontal motion, gravity has basically very little influence on it, because you're not changing your gravitational perspective in it. You're all at the same level. When you're falling or going up or down vertical motion, gravity plays a big part. That's what's pulling you downward, or when you throw something straight up, it's pulling it back down. Horizontally, gravity has basically very little effect. So, we're going to talk about falling motion, falling objects to begin with. That's when an object, this one, initially at rest, and it's released, okay? And what happens? Well, in the first, now this is probably, and by the way, these are not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 balls that they have lined up here. Nothing like that. This is one ball, but what they did, they set up a camera in a perfectly pitch dark room, okay, and had somehow this ball attached at the top. Okay, I don't know how they did it, but somehow attached at the top. And the instant that's released, they start a strobe. Oh, and by the way, they have a camera with the aperture open, the film being exposed, but in a perfectly dark room, nothing's hitting the film. No light is hitting the film. And at the very instant they release the ball, they start a strobe light. I think it's about every 1/10 of a second. And what you're doing, you're seeing that image of the ball as it's falling every 1/10 of a second. So the time interval is the same, but notice the distance that ball has traveled is very short here, a little bit longer here, a little bit longer there, a little bit longer there, and longer, and it's getting longer as it falls. So it's going a greater distance in the same time period. Okay? Now this is, I don't know if anyone had discovered it before Galileo, but I know Galileo worked with this concept a lot. And he came up basically with a formula that the distance that the ball has fallen is related to or proportional to the time squared. Not the time. If it was proportional to time, it would be the same distance for every interval, right? Okay? It's not. It's increasing with each interval, so that's with the time squared. In the first second, it moved a certain or first tenth of a second. In the next tenth, it moved a little bit further and a little further and a little further. So this is the basic distance for falling objects. Distance is related to 1/2 of the acceleration times the time squared. And that's basically how we define acceleration, okay, by making that observation. Now this is two caveats here, two conditions here. Number one, the initial position is 0. You're measuring this from the top, going down. So initial position is 0, and number two, initial velocity is 0. You're not throwing the ball down or throwing it up and then it coming back down or anything like that. You're releasing it from rest. And that's why neither initial position nor initial velocity shows up here. The acceleration is all that shows up here. Now, anywhere on the surface of the Earth, guess what acceleration that is? Acceleration due to gravity. Due to gravity. Now, I don't think we've hit that yet, but I want to mention it because it's coming up over and over again. All right. Seems like there should be a slide there, but there's not one. There is a little derivation here of how they got to that equation. And frankly, there's nothing wrong with it. It's a perfectly good derivation. This is on page 36. Okay? Before I get to that, though, let me mention this about falling objects. There's a concept applied here. Galileo concluded that all objects fall together at the same acceleration when the upward force of air resistance is removed. It would be difficult to remove air from the room, but it's possible to some experience, blah, blah, blah. So they take, there's a few examples here. Some of them are pretty good. In fact, one of them I think I did in class last time, didn't I? The piece of paper and the other piece of paper. I wadded this one up. Did I do that in this class? I did. Okay. That may have been time before last or sometime. Okay. So anyway, Galileo concluded that light and heavy objects fall in the same free fall as long as air resistance was taken out of the picture. Okay. Now, do y'all think it's worth me going through this derivation of this formula? I'll be glad to if you want to. No? Okay. Okay. Just understand that. What I will do, though, is give you the fuller equation. Like I said, this is determined by two things. One, initial position is 0. Second, initial velocity is 0. To give you the fuller equation, when those are not the case, here's what it would be. Let me get my pen set up. Okay. D is equal to D0. That's if you started at some position not 0. Okay. Plus V0t, that's if you gave it some initial velocity not 0. And then the last part is this part, plus 1/2 AT squared. So if you didn't have initial position 0 and initial velocity 0, then you'd use the bottom formula, okay? But with this one, initial position and initial velocity 0, yeah, that one's perfectly fine. All right. All right, I think the next slide coming up is figure 212 in the text. Let me see if that's true. Well, no. A couple definitions, then it's coming up. So what we mean by free fall is this. Falling under the influence of gravity without air resistance. You never have that happening on the surface of the Earth. There's always air resistance. But as long as the velocity isn't huge and the object is fairly aerodynamically shaped, then you can usually ignore air resistance. Once the velocity gets very large, though, air resistance really comes into play. So, that's what we mean by free fall. We're assuming no air resistance. Now, as in Galileo's formula you just saw, the distance is proportional to the time squared. Not to time, but to time squared. Okay? Now, with that, since the distance is proportional to the time squared, the speed increases linearly with time. Now this, you can't see this, that it's linear, but that is the case. It increases with time, and it's a linear relationship too. Now, you couldn't see that exactly from the last, but you could easily imagine it. Okay? Because the speed, because the distance is increasing by sort of a fixed amount each time, the distance increasing by a fixed amount, that would indicate the speed is increasing linearly, because it's not getting way bigger, but it's a linear response. You have to almost understand the math of it to realize that, but that's what that means. Okay? So speed is increasing linearly with time. Same length of time go by, same amount of speed increase. The trajectories exhibit up and down symmetries. Now, that may sound like a confusing sounding word or phraseology, but here's what it means. If I were good enough to have been at the bottom of this and thrown the billiard ball up so it just stopped right as it touched the plate, you wouldn't be able to tell whether this picture was falling down or going up. Okay? But I had to be that good so it just touched the plate just as it was stopping. Not that it stopped when it hit the plate, but it did that. In other words, the motion up and the motion down would have taken exactly the same picture. Exactly the same picture. If I had thrown it just so it would touch the top but not bump into it when it reached the top. Okay, that's what they mean by trajectories exhibit up and down symmetry. The same stuff that's going on as it's going up is happening as it's going down, just in reverse order. The acceleration is the same for all objects. That's what Galileo concluded, and that's what we understand to be the case too. As long as you're dealing with free fall. Okay. Okay, I know you're in here, you're hiding. But Brenda's, right? Okay. All right. Anyone else come in since I called roll? Okay. All right. Now, acceleration is the same for all objects. Whether the object's going up or coming down, it's a constant acceleration. Which is, if you think back to what we talked about before, what we mean by uniform motion. Okay? The speed is increasing linearly with time. That's also implied with uniform motion. Okay? Constant acceleration. There's the formula again. The distance is proportional to time squared. Why they took two different slides to do it, that's fine. It still works. Okay. Now here's an application of it, and this is the one that's the figure in your book. So what if you were way up in a 1, 2, 3, 4, 5, 6, 7, 8, 8-story building, on top of the roof of an 8-story building, okay? And you were to release something from up there at a given time, okay? Notice I said release, not throw it up or throw it down or throw it out. Release it, drop it from rest, okay? Now, in the first second, it would fall 4.9 meters, which is almost 5 meters, which would be, this room is about 3 meters tall because I'm a little less than 2 meters tall, and there's about another meter above me, so it's about 3 meters tall. So this would be 5 meters. That would be about a story and a half of the building. That's how far it would fall in the first second. Whereas the second, after 2 seconds, it's falling almost 20 meters, okay? So 4 times the distance that it did in 1 second. Well, proportional to the time squared. 1 second it went so far, 2 seconds, 4 times as far, okay? After 3 seconds, close to 45 seconds, which would be 9 times, so you're going as the distance squared. And in 4 seconds, it would be 16 times, okay, how far it traveled, okay, in just 1 second. So it's following as the distance is time squared. And here's where they throw this in. Have we hit 9.8 before? We have, okay. 9.8 is in the metric system, the acceleration due to gravity. 9.8 meters per second squared. Okay? Multiply that by time squared, second squared, and you get meters. And 1/2 of 9 times 9.8. 9.8 is almost 10. Half of that is 5. That would be just short of 45 meters. And that's exactly what we see there. Okay. Now, this is why they tell you, I've only been there once, okay? Have any of you ever been to New York City? Okay. What's probably the biggest attraction in New York City? And as far as being tallest attraction in New York City? Yeah, what building's that?
I don't know, the building.
Yeah, all the buildings are pretty, a lot of them are really tall. The Empire State Building, at one time was the tallest building in the world. And then for a very long time was the tallest building in this country. Now it's none of them, but it's still a very tall building. So we did go up to the top of the Empire State Building. And boy, the elevator trips are long enough, okay? It takes a long time to get up there, even with pretty fast elevators, okay? And you have to go up so far in one elevator, move to another part, go up some more. It seemed like it was 3 different elevators it took for us to get there. But at the top, in most tall buildings, they'll say this: please do not throw anything from the observation deck, okay? Why? Because there are cars down here. And if you were even to throw a penny off the Empire State Building, the speed that it would have by the time it reached the ground would be pretty great. And it could easily damage a car, a windshield, something like that, or a person, okay? Falling on their head, that could give them a concussion, if not a broken skull. It's amazing how much the speed. Now, in reality, air resistance, you don't ignore it anymore. There is, it will slow it down enough so it's really not as bad as you would expect, but it's still pretty bad. Okay, so this is the distance and acceleration, or distance versus time, with acceleration being the proportionality constant, or involved in the proportionality constant. Okay? And by the way, that derivation I was talking about, it gives a reason for the 1/2 being in there. But let me say this, I think I've said it before. Anytime you have a formula in physics, not anytime, most of the time when you have a formula in physics, that the primary variable is squared, you can expect to see a 2 in the denominator. Now they give one explanation for that now in the text. That's what I was asking if you wanted me to go through. But the real reason is because when you do an integration in calculus, that's the integration constant. And since y'all haven't had calculus, or I guess most of you haven't, and probably never planning to have calculus, that's sort of a moot point here. But that's really where that 1/2 comes from. Their derivation here gives a good approximation of why that 1/2 is there. But it really is coming from an integration constant. Okay. So this figure looks very similar. The only difference is now we're looking at the speed And the speed varies directly as the time. The velocity, the final velocity, is a times t, acceleration times time. Varies directly with the time, as it says here, linearly with time. Not with time squared, that's the distance proportional to time squared, linearly with time. So in 1 second, it's at 9.8 meters per second. After 2 seconds, it's 19.6, exactly twice the speed. In 3 seconds, it's exactly 3 times the speed, and in 4 seconds, it's 4 times the speed. So something thrown off the Empire State Building is going to take a lot of seconds to get down to that, because this is what? And what did I say, 8-story building? 1, 2, 3, 4, 5, 6, 7, 8. And if you're talking about a several 100-story building, that speed could be going quite fast. Okay. Now, it won't be as fast as you expect because of air resistance, but it's still very, very fast. And if a penny or a dime or something that you were to drop were to do like this rather than this, it goes even faster because the air resistance in this orientation is very, very low. Okay. So that's illustrates speed increasing linearly with time. Okay. Now, before we go to compound motion, there's a blurb here on page 37 on a bicycle racer's edge. It's not just the bicycle racers. What they're talking about here is basically we're talking about any kind of racing, and what they're illustrating here is the concept of air resistance. Okay? I don't know if you've noticed it, but have I asked this question before? Any of you been to Talladega? You have, during a race? Okay. Is it usually the guy who jumps out in the lead first, the one that wins the what race? No. Wouldn't you think it would be? But it's not. Anyone know why?
Because there's no air up there in the front. I mean, there's clean air, but there's no force.
Okay. Actually, what it is, second?
All the way to the front.
You get behind the other car, that air resistance pushes their car down and makes it give them traction. They can go faster. They get up.
Okay.
Getting a groove. I mean,
Yeah, that's right. Actually, you're drafting on the previous guy. Okay? Because if he's going along, he's meeting all the air resistance. But if he's sort of opening a little place and you can draft in behind him, then you can get much better gas pump. He's going to run out of gas before you will. Okay? And the bicycle racers here, they kind of line up. Because it's the guy in front who's always breaking the air resistance first, and then the others are drafting on him. And runners, when you have these, now if it's a 100-yard sprint or a 100-meter dash, whatever you want to call that, they just run as fast as they can down the thing. They aren't going to get behind anybody because they want to be first. Okay. But when you're doing any kind of distance thing, whoever's in front generally is going to lag behind toward the end.
You talking about the time race?
Okay, all of them are timed, but very short distances you just get there. Okay, but anything of any length, they tend to try to draft on each other. Okay. One exception for that, and y'all probably don't remember, there was a horse back probably 30, 40 years ago named Secretariat. You remember the name? Yeah. That horse, it didn't seem to matter. It liked to be in front, and it was the fastest horse on the track. No matter what field it was in, that was a super horse. And he would just take off and go. And none of the others could get close enough to draft on him is the problem, because he was that fast. And they kept saying, well, he's a sprinter. He won't win the next one because it's a longer race. He just won by a longer margin. That was all. I mean, I've never seen a horse do what he did. Most of the time, whatever starts out in the lead, not's going to make it at the end because it just runs out of gas. you literally, you expend so much energy breaking that air resistance. The Secretariat didn't matter. He was out there and gone. Okay. Now, so, but of course somebody was riding him, telling him what to do, but they couldn't even slow him down. He just didn't want another horse get in front of him, so he took off. Okay. Now, it's not just cars, bicycles, runners, or even racers like that. Have you ever watched birds fly, especially geese? How do you notice they fly?
Back,
How do you mean?
like forming like an arrow.
Yes, exactly. And why they do that, the one in front is kind of braking, and then the others are following in his wake, her wake, whoever it is. And literally, if you watch them long enough, if you have the opportunity to do so, you'll see that after a while, that bird will then drop back and another will move up. And they keep that up. So everyone takes his turn leading the V, because they're going to wear out after a while, and they go to the back, and they keep doing that. So at Talladega and other places like that, they have teams out there, don't they? It's not just every runner against the others. They're in teams. And the team is going to have someone driving in front of their star so that star can draft on them as long as possible. Okay? And then at the end, he takes off and goes, and does. Okay. So that's what that's about. Read the closer look. It's a really good article. And then also at the top of page 38, there's a bigger blurb, I mean, not bigger than that one, but more said about free fall. So I will let you take a look at that. So let me also back up a slide or two. This looks like a good one. And let's do example 2.7. Okay? A rock that is dropped. When you hear the word dropped, what does that imply to you? Hear the word dropped, what does that imply?
Distance.
Huh?
Distance.
Okay, it's going to be dropped. It's going to go a distance. But what does it mean to drop it as opposed to throwing it? What's the difference there? Say again? Free fall, which means what is the parameter that you know when you say it's dropped rather than thrown? The initial. Okay, well, yeah, there's no force. You got that. Well, force due to gravity, but that's all. But which one of our motion parameters are involved? Speed. What about the speed? Initial velocity is 0 if you drop it. It's not 0 if you throw it. So as soon as you read that word dropped, then you know VI is equal to 0. Initial velocity is equal to 0. A rock that is dropped into a well hits the water in 3 seconds. So that's your time interval. I like to call it delta t. The book just calls it t. That's 3.0 seconds. Okay? Ignoring air resistance, how far is it to the water? In other words, how deep is the well? Okay? How deep does that well go for it to take 3 seconds for it to be dropped from the top until it hits the bottom? What's our distance formula? D is equal to 1/2 A T squared. Perfect. Now what does that A stand for? And what is the acceleration in the SI system? In those last slides, what was that acceleration? It's hard to see here because I've written over it. The acceleration is? 9.8. Now, they left off the units. Shame on them. Okay? It's 9.8. What are the units? Meters per second squared. Velocity or per second, acceleration per second squared. times the time, which is 3.0 meters squared. So this would be 1/2, well, 1/2 of 9.8 is 4.9 meters per second squared, times, what is 3 meters squared? 3 squared is 9.0, and then you square your units as well, meters squared, and what am I talking about? The time is in seconds, not meters. Goodness gracious. The old gray cells are messing up today. Goodness, my pen won't come back. There it comes. Second. So it's second squared. So the second squareds go out, and you're left with 9 times 4.9 is, anyone do that quickly? Meters. Okay, we only have 2 significant digits here, so we'll make that 44 meters. We don't really have precision to say we got 3 digits, so we'll say about 44 meters, which is pretty far. That's a pretty deep well. That would be half a football field deep, because a football field is 100 yards. That half of it would be 50 yards. And a yard is a little bit shorter than a meter, so that's very close to half a football field deep. That's a pretty deep well, okay? That would be fairly close to 150 feet deep. That's a pretty deep well. I hope I didn't have to dig it. Okay. Now, they give you 2 ways to solve this. We did it the first way, and that makes, to me, the most sense. They show a different way to do it using average velocity, and it's kind of convoluted, so I think this is the most direct way. But if you need to see it or would like to see it, knock yourself out. There it is. All right. Any questions? All right. Ready then for compound motion. So the first motion we talked about horizontal motion, then we talked about vertical motion. Compound motion is the third kind, vertical, horizontal, and a combination of the two. It's some vertical and some horizontal. The lab we do today is going to be on compound motion. Okay? And this is Chris, right? Okay. All right. The one we do today will be on compound motion. Now, sometimes this is given the name projectile motion. Now, a projectile is not just a weapon, okay? I think when I think of projectile, I think something shooting somebody at something at somebody else, okay? It's not. Projectile motion is any object that's projected into the air of any way. Now, understood here is that you're in a gravitational field. On the surface of the earth, you're in a gravitational field. And when it says into the air, that means there is some air involved. So we're going to basically ignore the air resistance. Good, better, and different, we're going to do that. So here projections could be anything. A ball. Shoot a basketball. That's projectile motion. Hit a golf ball. Projectile motion. Throw a football. Projectile motion. Hit a ping pong ball. Projectile motion. You know, anything thrown or tossed or hit into the air is projectile motion. Here are the basic observations. Number 1, gravity is always active. Do you think gravity only is acting when the ball's coming down? No, gravity is acting on it when it's going up. That's what slows it down, okay? Otherwise, it just keep on going up, okay? So gravity acts all the time. From the moment it leaves your hand, the object that's hit it, or whatever, okay? Now, the acceleration, g, is independent of the object's motion. It could be going up, coming down, doing whatever. Stuff, before you sit down, let me give this to you. It was left over from last mini term. I started to recycle it. I thought, wait a minute, I'll see him. I've had it with me ever since, and I've forgotten to give it to you. Okay. And Seth's here. Okay, good deal.
Can I get my quiz?
I'm sorry?
Can I get my quiz?
What quiz is that?
From this morning, the 8:30 class.
Okay, I don't have it with me, because
Okay.
that's in my other thing.
Well, can I get it Thursday?
Yeah,
Okay.
that'll be fine.
Okay.
Okay. I can't believe someone coming in and interrupt the class like that. But anyway, the acceleration g is independent of the object's motion. That's what I was saying before. When you throw the ball up into the air, acceleration due to gravity is acting on it just like it is when it leaves your hand, when it's on its way up, when it reaches the peak, when it's on its way down. The acceleration g, independent of the object's motion. Doesn't matter where it is in its motion, the acceleration due to gravity is the same throughout. Okay. So with those two things in mind, here's what we mean by projectile motion, which is just another way of talking about compound motion. Let's start with a perfectly vertical projectile motion. Okay? If you throw a ball straight up, I mean no horizontal component at all, throw it straight up, as soon as it leaves your hand and it's left the force that you've given it, then it's going at some speed. Initial velocity is not zero then, because you're throwing it up, and as soon as it leaves your hand, the velocity starts decreasing. Okay? And it decreases all the way up until it reaches zero. At the very peak of the motion, it will have a zero velocity, and then it starts coming back down. Well, guess what? A change of velocity is an acceleration. It's the same acceleration acting on it going up and coming down. It slows as it's going up, stops at the top, and then accelerates down. Was accelerating as it went up, it's just a negative acceleration. When it stopped, that was just momentarily because it was still accelerating downward the whole time. The force of gravity acts downward throughout the motion. Okay? Now, the only exception to that, if you are firing a rocket with enormous thrust upward, that you're going to escape the gravitational field, then, yeah, it doesn't act because it's decreasing it. But when anything you can throw, okay, it's going to be constant throughout. All right. How about horizontal projections? I'm going to throw it perfectly horizontal. Is gravity acting on that one?
No.
No, of course it is. It's pulling it downward. If I throw something straight out there, as soon as it leaves my hand, it starts ever so slightly going downward. Okay? It is going down the whole time. Therefore, when you throw a football, you don't throw it straight at somebody. You throw it with a little bit of an arc. You have to. You don't shoot a basketball by aiming right for the rim. If you do, you're never going to get it. You got to have an arc in it. Every time. Always. Okay? So, horizontal velocity okay. Horizontal projectiles, the horizontal velocity doesn't change. In a vertical projectile, the velocity is always changing. Because you throw it straight up, as soon as it leaves your hand, the velocity is decreasing. Well, if I throw it straight out, horizontal, then the horizontal component of the velocity isn't going to change. It's always going to be the same. It's just as soon as it leaves my hand, it starts dropping. Ever so slightly, but it starts dropping, and that's a vertical component. So the horizontal velocity remains the same, neglecting air resistance, of course. And as long as they don't throw it too hard, it doesn't have too large a speed, that's pretty good. It's still a vertical motion, taken with vertical motion, and you have a curved path. So, any of you baseball players follow it at all? Okay, there's two major types of pitchers. There's many others. Two major types. Of course, there's the fastball, and then the curveball. And guess what? Even the fastball is curving. It's just not curving much because the initial horizontal velocity is so great, it doesn't have much time for it to curve. But a curveball is always thrown at a slower speed, and then it has a drop to it, okay? And that's basically what now you also try to give it a spin so it is also curving in or out of a batter, but the main thing is curving down, okay? Now, so there's always a curved path. As soon as it leaves your hand, it does start dropping, ever so slowly, but start dropping. So let's go back to this one. Now, this is a really gross example, but it's true. Most of the time you'll see this in other countries, but occasionally you'll see it here in this country. Something happens and people are out celebrating and someone fires into the air. A really dumb move, okay? Because guess what? What if you fired it absolutely straight up, okay? Say again?
Then it come back and hit you in the head.
Yeah, it certainly will. If you don't move, it's coming back and hitting you. Now, what speed will the bullet have? Greatly reduced?
Probably should. I don't
Huh?
know. I don't know. That's a trick.
Actually, not much reduced at all. The only reduction would be because of air resistance. But, get this. Fire, just like throwing something into the air, fire something into the air, straight up. As soon as it leaves the barrel, it's going at a very high speed. Anyone, a shooter that knows about the speed of a bullet?
How many feet per second?
Yeah, anything like that, miles per hour or whatever. Really fast though, okay?
Fast speed.
So let's just assume 100 miles an hour, okay? Does that seem reasonable?
1,000 feet per second.
1,000 feet per second, okay, 1,000 feet per second. Does that seem reasonable?
Yeah.
1,000 feet per second. What's that?
Like once a gun is fired, you got like a half a second, like 0.5 seconds to move out there.
You move out of the way before it comes back
Yeah,
down?
you got that.
Okay.
Will hit you.
Okay. All right, so let's say 1,000 feet per second. You fire it straight into the air, 1,000 feet per second. In 1 second, that's going to slow because in the U.S. customary measure, the acceleration due to gravity is 32 feet per second squared. So in 1 second, it's going to slow from 1,000 feet per second to 968 feet per second, because it slows 32 feet per second each second. So in the next second, it's going to drop again to whatever, subtract another 32. And then in the next second, subtract another 32. And it's going to keep going like that, subtracting 32 feet per second every second that it is going up. Okay? But then when it reaches the peak, the top, it's slowed to 0. And then it starts coming down at the rate of 32 feet per second. So that first second that's coming down, it's going to go up to 32. The next second, 64. And it's going to take the same number of seconds coming down as it went going up, because it was slowing going up by 32 feet per second each second. Coming down, it's speeding up by that. So when it gets back to your level, 1,000 feet per second, or something awfully close to it. Air resistance will slow it a little bit, but not a whole lot, because bullets are pretty aerodynamic. Okay? So, everything that's shot up is coming down. Even if you don't shoot it straight up, that would hit you in the head and kill you. It's going to come down somewhere at basically the same speed you shot. It's going to slow as it's going up, but then increase the speed at the same rate coming back down. So, I think it was the very first fall after we moved to Birmingham. I think it was. We heard the story. Y'all may not have been born yet, but we heard the story that some man and his wife and little kid were in their pickup truck driving on one of the interstates going east or west, somewhere between here and Georgia, I think. And they thought they heard something and just glanced back at the baby. She was in the jump seat in the back kind of thing, whatever, club cab, whatever. And she seemed to be sleeping, so they didn't think of anything. And when they went to stop, either got to their destination or stopped for gas and went to get her out, they saw she had gotten a bullet in the back of her that someone, no one, it wasn't intentional, it wasn't anything else, someone was firing a weapon, either shooting at something or just doing target practice or something, and it could have been a long way away and just happened to be into the air. It slowed as it went up, but it gained speed when it came down. It just happened to hit the back of the window right where the kid was. So everything that shot up in the air is going to come back down at basically the same speed at some point. Somewhere up there, it's going to be at almost zero velocity if you fired it straight up. If you fire it out this way, whatever that initial velocity, horizontal velocity was, that's not going to change. The vertical velocity will change. Change is going up, slowing down, but coming back down, it speeds up again. So at the bottom, it's going to be almost the same speed. Now, here is a really bizarre example, and you may not think it's true, but it is. It has been shown before. If she was firing an arrow perfectly horizontal, now that's not going to hit the target perfectly horizontal, it's going to miss it, so she needs to fire up. But if she fired it perfectly horizontal, and he was standing there watching her, and the minute she released the string, he dropped an arrow perfectly horizontal. They're going to hit the ground at the same time. If they're on a level field, they're going to hit the ground at the same time. Amazing but true. Hers is going to go way out there, but they'll hit the ground at the same speed. Because the acceleration due to gravity does not change. It's independent on whether it's got any horizontal velocity at all, but it's independent. Now he gives it zero horizontal velocity, so all this is going down. She gives it a huge horizontal velocity, but the vertical velocity is going to change the same way his does. And the horizontal component, though, never changes, does not change, okay? So vertical motion occur in parallel. Vertical motions occur in parallel. The arrow has an additional horizontal component. The one that she shot, the one that he dropped, does not. But they strike the ground at the same time. Hers is way out there, so it was going much faster than his, but the vertical movement is the same. If she shot perfectly horizontally, and he just released it at the same moment, they'll hit the ground at the same time. Amazing but true. Any questions? Okay. So here's the passing of football. The only force, now, whether you're throwing a football, a baseball, a basketball, hitting a golf ball, a ping pong ball, whatever, okay, the only force acting on it is when it's in touch with your hand, okay, or, you know, whatever the club head or whatever it is. It's the only force. As soon as the ball leaves your fingertips, or leaves the bat, or leaves the golf club, or whatever it is, then the only force acting on it is gravity, and that's pulling it down. So whatever initial velocity you have in the horizontal direction, it's going to keep that velocity until it ultimately hits the ground. The vertical velocity, though, is always going to decrease on the way up and speed up on the way down at exactly the same rate. The vertical velocity decreases as it goes up, stops at the peak. Horizontal is still the same, whatever you gave it, then increases on the way back down. The horizontal motion is uniform. And the combination of those two motions is what we call a parabola. Okay? Every baseball you throw, every basketball you shoot, every football you throw, every golf ball you hit, whatever, they're all going to follow the path of a parabola. While they're in the air, they follow the path of a parabola. So here's the guy, okay? Quarterback throws the ball, and he always throws it somewhat upward. You don't ever target to go straight at the guy. Really short pass, you can, and the guy can pick it up from here. But if it's very far, it's going to hit the ground before he can even react to it, okay? So there's always a vertical component, okay? And whatever is given going up, the horizontal velocity does not change, okay? Okay, but the vertical velocity, you gave it a large one to begin with, it decreases, stops here, and then starts increasing, going down, and he catches it basically at the same speed he threw it. Okay. Now, there is some air resistance involved, but we're going to ignore that. Because what are your most effective passes usually? Spirals, where the ball just does like this. That minimizes your air resistance. There was an old quarterback for the Washington Redskins who threw one of the ugliest passes in pro sports I've ever seen. And his balls wobbled like crazy. He was amazingly accurate and had a really good passing record, but his balls were not very pretty. Those perfect spirals, they are going to be the most predictable. But the acceleration is downward throughout. There is no acceleration horizontally, or, well, there is vertically because of gravity. Once it leaves the hand, then the acceleration is constant. Horizontal acceleration. Gravity is always pulling it down. Okay. All right. Pretty sure we should have some more examples here. Let's see if we can find them. Okay, I haven't been turning the pages as I should. There's a science sketch, which to me is probably a bit on the lame side, but you can look at that if you want to. No, there aren't any problems on this section. That's rather strange. We'll be doing some in lab, though, and we'll get there. And they mention here a moving airplane, but this really is any device. Have any of you been to a, what do they call them? Places like Six Flags and these other places that have the rides and the roller coasters and that kind of stuff. Okay, have you been on those devices? What is it that makes them exciting? Is it the speed that you're going? It's the curves. It's the changes in speed. When you loop-de-loop, you're actually going pretty slow at the top, okay? It's the change, it's the accelerations that you're paying for. Now, if you've ever been in a plane, you may be going at 500 miles an hour, but you don't really notice it unless you change your speed. Like you had an air turbulence or something, then you notice that. But when you're in straight level flight, you feel like you're on the earth. You don't sense any motion at all. So the things that are exciting on the roller coasters or whatever is when you're changing your speed, you're accelerating. Okay. I guess that leads into the three laws of motion. Now, what we've done up till now is going to be today's lab. This starting now is going to be Thursday's lab. Thursday's lab is going to be pretty short. I think you'll find that you can do it pretty quickly. Okay. Today's lab is not going to be as long as the first lab, but maybe not quite as short as the last lab. It's about the same as the last lab. All right. First detailed, the three laws of motion, first detailed by Newton. Now we're going into these each one separately, and when we get to the first law, we'll see it was actually done by Galileo. Newton just refined it. Okay, Newton lived 1564 to 1642. So what is that? 78 years or so. And if I'm not mistaken, he was born on Christmas Day on 1564. Sort of sadly, his dad had died just a month or two before he was born, so he never knew his dad. And also sort of sadly, I mean, not totally sadly, but his mom remarried sometime when he was a young child, but the new father really wanted to deal with his children, not with somebody else's. So Newton was sent to live with a grandmother or an uncle or something like that. So Newton had a pretty rough time coming up. He wasn't very wealthy, but he was incredibly bright. And somebody, I think it was an uncle, recognized his brightness and brilliance, in fact, and said he needs to go to Oxford. They couldn't afford him to go to Oxford. So he basically, in a sense, paid his way through, I think it was Oxford or Cambridge, whichever it was. It was one of the great universities in England. There's two big ones, those were it. One of those two. And he paid his way through school, basically acting as a servant for the rich kids. He shined their shoes, folded their clothes, made their beds. That's how he worked his way through school. Of course, in very little time, he surpassed every professor there in knowledge. He just ate it up. And soon they said, okay, why don't you start teaching? And this one guy, his math guy, said, you take over my chair because you passed what I'm able to teach you. You go from here. Incredible genius. Okay. Isaac Newton. While he was developing these three laws of motion, he had to come up with a brand new math to do it because the existing math of his time wasn't adequate to describe the motion to the detail he was wanting to do. So he invented an entirely, totally new field of mathematics while he was his thing of motion. Okay, three laws of motion. Oh, and by the way, he came up with a brand new description and law of gravitation no one had even conceived of before. Oh, and about the same time, he was also studying light and came up with ideas and theories of light that are still in effect today. No one else has even come close to anything like that. Quite a genius. Okay? Now, this is a rather bizarre spin on it, though. After he had finished college, university, I think it may be Cambridge. I keep saying Oxford, but I think it may have been Cambridge. Okay? But whichever. And he went on faculty. Okay? And he was beginning to get his feet wet. And I don't think it had been more than about 3 or 4 years since he was given the position that something happened. The bubonic plague broke out in England. It had broken out in Europe earlier, and I mean, untold millions of people had died. No one knew what to do with it. You know, it was a disease they didn't have any way to treat. People just were dying like crazy. But what they had learned from observing what had happened in Europe is that the people in the cities were dying much more frequently than the people out in the country. They didn't know why, but when it broke out in England, and here were the very top minds in the country, all inside, I think it's within the city limits or very close to city limits of London and Cambridge University, and they said, wait a minute, if we keep them here, there goes a whole generation of knowledge. Let's shut the school down, send them home to the countries. Maybe they'll survive. That's what they did. So Newton was sent home, and it seemed like it was about 3 years that the college, the university was closed completely. It was during those 3 years, when he didn't have teaching responsibilities and university staff and other responsibilities, he just thought and wrote and experimented. That's when he got most of his life-changing, for all the rest of us, discoveries made because of the bubonic plague. If he had been at university, it may have taken him decades to get done what he did in those 3 years. Pretty amazing. Okay. But in these three laws of motion, the essential idea is that of forces. They show up in all three of the laws. Now, if you recall, the key concept for the whole chapter was having to do with forces. Let me read it to you again. A net force is required for any change in the state of motion. And basically all we've done up till this point is talk about motion. Distance, displacement, velocity, speeds, and accelerations. Now we get the main idea here, the forces. Okay, the essential idea. So here's the first law of motion. Now, sometimes this is called the law of inertia. Now, we mentioned inertia earlier, I think, didn't we? Okay, I thought so. Okay, inertia is that characteristic capability of an object to try to resist its change of motion. Okay? That's if something's at rest, it tends to stay at rest unless it's acted on by an unbalanced force. If something's moving, it tends to keep moving in a straight line, same velocity, unless it's acted on by an unbalanced force. That's the first law of motion. Every object retains its state of rest or its state of uniform straight line motion unless acted on by an unbalanced force. There's the forces. Unless acted on by an unbalanced force. Now, this was not Newton's original idea. Galileo came up with that. But Galileo was down in Pisa, Italy, where the famous Leaning Tower is. They claim that that's where he did his experiments, off the top of the Leaning Tower, dropping the rocks from there. And he dropped them in different masses, a very big massive rock and a little bitty rock. Dropped them from the top of the tower, and sure enough, they landed at the same time. Same instance, his assistant was on the ground. Or he sent the assistant up and he dropped and he measured, yeah. But that's the law of inertia. That unless there's an unbalanced force, everything travels, maintains a state of rest or a state of inertia. Inertia is anything that resists a change of motion. So even if something is moving at a speed, like if I threw a bowling ball at Wyatt back there, he probably is going to want to move because he doesn't want to change that bowling ball's state of motion. That would be a hard thing to do. If I threw a ping pong ball at him, he probably wouldn't care, okay? Because inertia depends on the mass. And we'll get to that a little bit later. So that's the first law of motion. Okay, here's sort of an example of this. Have you ever been on a bus and you didn't have a seat, so you had to stand in the aisle there, and if the bus took off all of a sudden, you say you were thrown back, right? No, you weren't. You just tried to stay where you were. The bus moved out from under you. Literally is what happened, okay? You tried to maintain your state of motion, which was right where you were, at rest. And it moves, and you feel like you're thrown backwards. No, the bus moved out from under you, okay? Or, let's see if they give this one. I think they do. If you're now moving along pretty nicely, you don't notice it because you're not accelerating, you're just moving, and you're just standing there, maybe not holding on to the strap of the pole like you're supposed to because it's fine, and all of a sudden the bus turns. You say you're thrown against the outside wall. No, you're not. You're trying to maintain your state of motion. The bus just cuts in front of you, okay, literally. And that's what happens with that. So again, your inertia tries to keep you moving the same way. It's just the bus cuts in front of you, okay? So that is what inertia is, that tendency. I can remember several years ago when I went, about this time of year, maybe a little bit later, the grass had just started growing, and I went to break out the lawnmower and get ready to cut the grass the first time in the spring. And I noticed when I put the gas in the lawnmower, it started running out. There was a leak in the fuel line. And I didn't want to go buy a new lawnmower, so I called around. I knew I'd seen someplace that repaired lawnmowers, so I called them. They said, yeah, bring it. So I put it, I had a pickup back then, so I put it in the back of the pickup, and I tried to chock the wheels, but the chocks didn't work very well. And every time I accelerated, boom, I'd hear it hit the tailgate. And when I slowed down, boom, it would hit the front. And when I turned to the right, boom, it would hit this side of that. It was just moving all over the place. But I said, I'm not going to stop and chock them again. I need to get mowing, so I went on. But that was inertia. The lawnmower was trying to stay right where it was, and every time the truck changed speed, changed direction, it would hit one of the sides or front or back. Okay? That's inertia. Okay. Let's see if there's a problem. No. we go straight to the second law. So the first law is an object tends to maintain its state of motion, whether at rest or in motion, straight line, uniform motion, constant speed, that kind of stuff, unless it's acted on by an unbalanced force. Newton's second law, though, says, and this is, Galileo didn't go this far, he said a force causes an acceleration. So in other words, if there is an unbalanced force, then you're going to change the object's velocity. And what is a change of velocity? What other parameter? It's an acceleration. An acceleration is a change of velocity. So if there is an outside force, it's going to create an acceleration. That could be slowing it down, speeding it up, or just any way changing its motion, changing its direction. Okay? Now, what is a force? Well, they jumped into it a little too soon here. I'm going to do these in a different order. A force is proportional. Okay, a force is proportional to the acceleration. We'll start there. Okay, remember when we did proportionalities? Okay, let's do it here. The force is proportional to the acceleration. Okay? Now, how do we change that proportionality to an equal sign? Anyone remember that from test 1, chapter 1? Equal k. At proportional to, you can change to k, where k is some proportionality constant, that acceleration. Okay? What is that proportionality constant? That proportionality constant is the mass of the object. That proportionality constant between force and acceleration is the mass of the object. The greater the force, the greater the acceleration for the same mass. But if you had a bigger mass, you're going to have a larger force for the same acceleration. So the force, the constant, proportionality constant for that proportionality is the mass. The proportionality constant is the mass. Okay? More force, more acceleration if you have a constant mass. But if you have more mass, you have a lower acceleration if you have a constant force. So that would be if I threw the baseball with the same force that I threw the bowling ball, which one's going to accelerate more? The bowling ball? I use the same force now, not throwing it harder. No, throwing with the same force, the baseball or the bowling ball, which is going to accelerate more? The baseball, for sure, okay? Because the bowling ball has more mass, it's going to take more force to accelerate the same amount. So the more mass, the less the acceleration. At the same force, the more force, the more the acceleration with the same mass. So that relates to this. Now the reason this is true is if you look at that, divide both sides of here by mass, then the acceleration is proportional to the force, or is equal to the force over the mass. So when the mass increases, the acceleration decreases. That's an inverse relationship, inverse proportionality. When the mass increases, the acceleration decreases, mass decreases, acceleration increases, for the same force, constant force. So the more mass, the less the acceleration. Does that make sense? Okay, builds on what we did last time. Let me take this writing off so we can see what they showed next. Ha! And here it is. So here is the formula I just had up there. Now this is what we call the net force. Another way to express it is total force. Okay? The total force. Now remember, accelerations and forces are vector quantities where the direction matters. So when we're talking about net force here, all the different forces act on it could be in different directions. The net force is the total force vector sum of the forces. That's what we're talking about here. That's going to determine the acceleration of the object. The total net force acting on the object, the vector sum of that is going to determine the acceleration. Okay. Now, let's look now at units. Okay? What is the SI unit for mass? Does anyone remember? That was on the first test too. SI unit for mass. Kilogram, perfect. How about acceleration? Just the units. Meters per squared, exactly. So forces are measured in kilogram meters per second squared. Well, that's a lot to say for a unit, right? So they give this a name. That name is a Newton. Guess what? Named after Sir Isaac Newton. And guess what else? Notice kilogram is a small k, g is a small g, meters is small m, seconds is small s. Why in the world is Newton capital N? Named after somebody, exactly. It's a proper name after somebody. So that's the unit we use in the SI unit to measure force. Mass is in kilograms, force is in newtons. Now, if we think back on the U.S. customary system, does anyone know the force unit in the U.S. customary system? The force unit.
Horsepower, or HP,
It's when you stand on the scales, what do you measure? Pounds. That's the unit of force in the U.S. customary system. But remember, mass is not usually used in the U.S. customary system. I did tell you that unit, no one ever uses it. Remember what it was? Like a slimy little thing that you found in your garden. That's not where it comes from. It has the same name, though. A slug. It's so uncommon, they don't even have an abbreviation for it. If you use slugs, you have to spell it out because there's no abbreviation for slug. Okay, so in the U.S. customary, what corresponds to mass for pounds in the U.S. customary is newtons in the SI system. But you know, on the grocery store, on the scales, what do they have on the scales? Either ounces and pounds or kilograms. They act like those are equivalent. They're not. Kilogram measures mass, pounds measures force, like a newton. So they really should have on those scales pounds and newtons. But no one knows what a newton is, if you're not in physics. So they use kilograms. Not the right thing to use. But on the surface of the earth, it only differs by a constant. That's all. Constant has units, of course, but they only differ by a constant. All right, let me move this out of the way then. So remember, Newton is a kilogram meter per second squared. Mass times an acceleration. Okay. All right. Oh, and by the way, that formula there can be, you can get up to 2 more formulas out of it just by manipulating it. What would those other 2 be? Anybody? Second, M is equal to F divided by A. Perfect. Or A is equal to F divided by M. Perfect. Now remember, these forces are your net forces. Okay, I like to call it F sub N for net force, which is the vector sum of all the forces acting on it. Now, let me give you a little bit of an example for that. Okay? Let's imagine you have an airplane, a jet plane, flying along in a straight level path at 500 miles an hour. Okay? Flying a straight level path, 500 miles per hour. What's the net force acting on that plane? If you don't know for sure, just give me some of them. You think it has a net force acting on it? flying along at 500 miles an hour, straight level flight. What's the net force on the plane? I can tell you exactly.
0.
0. Why?
It's not accelerating.
It's not accelerating. I said constant velocity, straight level flight, not changing direction, not changing speed. Its acceleration is 0. The net force on it is 0. Does that mean there's no forces acting on the plane? No, of course not. Because there's tons of air resistance. If you're flying at 500 miles an hour, you have an enormous amount of air resistance. Okay? No matter how streamlined that jet is, it still has air resistance. And I guarantee you, too, you got jet engines pushing you at that speed. Because otherwise, you wouldn't go at that speed because of the air resistance. So you got the engines pushing this way, but air resistance pushing that way. They are exactly equal. Net force vertically is 0. How about horizontally? Guess what's down here? The Earth. If the Earth's beneath you, guess what you got? Acceleration due to gravity. That's pulling you down. Down. But the shape of the wings and stuff like that is giving you lift. That's what keeps planes in the air. So exactly the weight of the aircraft. I mean, if this is a jet plane full of passengers, it weighs tons and tons. That's the weight pulling you down, but the lift is keeping you up. That has to be equal and opposite. So the net force acting on the plane is 0. Why is that? Because it's not accelerating. I told you it's straight level flight at a constant speed. Okay. That told you the acceleration was 0. If the acceleration is 0, net force is 0. That doesn't mean no force is acting on it. It means that every force acting on it has an equal and opposite force in the opposite direction. Okay. Now, let's go back to, and by the way, you can use the circles or triangles if you wanted to keep that formula in mind. I like the triangles, but either one of them is fine. You put the net force on top and the mass here and acceleration there, or vice versa. It works. Net force is mass times acceleration. Mass is equal to force divided by acceleration. Acceleration force divided by mass. Perfect. Any questions? Okay. Y'all don't let me run over. Okay, what is it? About 10 till 3? Is that right? Okay. We go to 3:45. All right. Is this a good place for the example? I think we'll do this before we get to the example. Okay? Newton's second law, the more mass, the less acceleration, just like we had a little bit earlier. More mass, less acceleration. All right, bottom of that one, top of this one. Okay? The focus is on the net force. Now, net force is 0 here. What are they talking about? Oh, here's what they're talking about. Here's a guy riding a bicycle. Now, he's not one of those racers. He's sitting upright. Notice all those racers were down like this. Why? Second? Less air resistance. This guy is just tooling along. Okay, but he's pedaling, and that is a force applied, but he's meeting air resistance and frictional resistance. So the sum of the air resistance and frictional resistance, if that's exactly equal to his net force, then his acceleration, well, the net force is 0. If one's in this direction, the other two are in that direction, and they're equal, the sums are equal, net force is 0. What's his acceleration?
0.
0. What's his speed?
0.
Constant. It may be 0, but if he has a net force, then the odds are he's moving.
Right.
Not net force, but he has a force applied. If he's meeting air resistance, that implies he's moving, so his speed would be constant, meaning 0 acceleration, but constant speed. And not changing direction, because then he would have a net force, because he'd be accelerating. Okay? Now, again, so in this picture, his net force here is 0. The total force against him is equal to his force applied. Net force is 0. Air resistance plus the tire friction match the applied force, no acceleration, constant velocity. There it was, in blue and white, okay, or something like that. Okay? Now, they don't show the next one. What if his girlfriend gets on a tandem bike, bicycle built for two, and she sits back there and he thinks she's pedaling, but she's not, but she weighs the same thing he does. What does he notice about his acceleration? It goes down. If she's the same weight as him, as we're neglecting the mass of the bicycle, then we'll say that his acceleration is cut in half because she's not adding any force, but you've just increased the mass. Okay? They don't show that here. And they go on to something else here. Okay? In the book, they show it. Okay? And notice she's not pedaling. Okay, if you have your book there to see. All right. Now, before we get to weight and mass, let's go find some space. There's some right there. Let's do examples 2.8 and 2.9. Then we'll get to weight and mass. Okay? A 60-kilogram bicycle. What is that a measure of? What does kilogram measure? Say again?
It measures thousands.
Oh, thousands of grams. What does a gram or a kilogram measure? What kind of unit? What kind of quantity is that? That's the mass, exactly. That's the mass of the bicycle, okay? Mass of the bicycle. Okay? And, oh, I'm sorry. 60-kilogram bicycle and rider. Okay, that's a heavy bike if that was 60 kilograms. So I'm going to take off the B. That's the mass of the bicycle and the rider. I can't get my eraser to work. There it is. Okay. Mass of bicycle and rider. I didn't read the problem far enough. Accelerate. So the acceleration here is 0.5 meters per second squared. That doesn't sound like a lot, does it? But it accelerates at 0.5 meters per second squared. Notice that is a good unit for acceleration. How much extra force was applied to make it accelerate? So in other words, what was the net force that you had to give it to create that acceleration? It's pretty straightforward. Say again? Yes, exactly. It's mass times acceleration, which is 0.5. Well, let's get the mass first. 60 first. I like to put the smaller number in front, but let's do it this way. 60 kilograms times 0.5 meters per second squared, and that gives you 30. Is that what you said? What units? Newtons, exactly. A kilogram meter per second squared is a newton. So that's the force, the net force required. Okay? All right. That would be what they call an extra force. If you're having a pedal anyway, just keeping it moving at a constant speed, you have to do an extra 30 newtons to get it to accelerate. That's why, where do you use most of your gas mileage in your car? Second?
Going up hills.
Speeding.
Oh.
Going up hills and accelerating.
Okay, that will certainly do it anytime you're accelerating. Whether it's from stop to 30 miles per hour or going up and down hills, you're accelerating to do that. Anytime you're doing that. If you're on cruise control on the highway at 70 miles per hour, you do have some that you're overcoming because you have more air resistance then, but that doesn't eat the gas mileage like in-city driving when you're going from 0 to 20 and 0 to 30. That's when you're accelerating. That's when you eat your gas mileage up. Okay? So it's the acceleration that does it. It's the fun thing at the carnivals, but it's also what eats up your gas mileage. So I think we can get out of this and do the next one. It doesn't relate to this one. It relates, but it's not got the same number. What is the acceleration? This time we're looking for acceleration. That's the unknown of a 20 kilogram cart. What's that a measure of? That's your mass measurement. 20 kilogram cart, if the net force on it is 40 newtons. So the F sub n is equal to 40 newtons. Now, in this case, I think I would change my newtons to the fundamental units, and what are they? What makes up a newton? What units? Okay, yeah, but what units for that? What's unit for mass? Kilogram, meters per second squared. Okay, that's what I would use instead of newtons here. Okay? So, what formula do we use?
A equals F-E, force net divided by mass.
Perfect. So that would be 40, and then use those units, kilogram meter per second squared, divided by the mass of 20 kilograms, and the kilograms go out, and what you're left with is 40 divided by 20. Second? 2. 2, and the units are meters per second squared, which is a great unit for acceleration, right? Okay. Now, I guarantee you this, you're not going to maintain that acceleration very long, because increasing at 2 meters per second, it's not going to take very many seconds before you're flying, okay? Because this is the acceleration. Your velocity is going up 2 meters each second that you're accelerating like that. So that's, your velocity is really going up fast. You're burning the gas if you're doing that. Okay, so 2 meters per second squared. That's a pretty high acceleration, by the way. Okay, there is a second law experiment, described in the book, and this is pretty good. It's certainly something, I wish we had time to do things like that, but we don't. We'll do something a little simpler. So let's now move to weight and mass. All right. Now, let's start with mass. We've already talked about it before. It's a quantitative, meaning you have units to begin with, quantitative measure of your inertia. We already referred to that the other way, that the bowling ball would have greater inertia than the tennis ball, okay? So, yeah, quantitative measure of inertia. The amount of matter that's there. Now, this, by the way, is not a vector quantity. It's just a scalar, just a number. No direction associated with it.
I have a question.
Yes?
For the acceleration, it always going to be 9.8.
So that the acceleration due to gravity, if you're anywhere on or near the surface of the Earth, yes.
Okay.
If you're on the Moon, no.
No.
Venus, no. Mars, no. Any other planet, or outer space, no. Okay. It's only on the surface of the Earth, but guess where we spend all over time? On the surface of the Earth. So anytime you need it in normal circumstances, yeah, it's 9.8 meters per second squared, or 32 feet per second squared. That's the U.S. customary. Okay. So, what weight is, though, is the force of gravity acting on the mass. Okay? So that gives us weight, which is a force. Now, this is net force. Don't confuse these. This is a net force. This is the force due to gravity, weight. Okay? But notice the similarity of their formulas. Equal to mass times acceleration. It's just that anytime you're on the surface of the Earth or anywhere near the surface of the Earth, your acceleration due to gravity is g, 9.8 meters per second squared. Whereas if a net force is giving something acceleration, that doesn't have to have anything to do with 9.8, okay? It's just that you're accelerating the baseball when you throw it, the bowling ball when you roll it. You're accelerating it as long as you're touching it and applying a net force to it. But the force due to gravity, that's weight, and that's mass times the acceleration due to gravity, that specific acceleration. Okay. So, as we mentioned before, pounds and newtons are equivalent measures. They measure force. They're not the same values, but they're equivalent measures. Whereas a kilogram is a measure of mass, and we don't even mention the measure of mass in the U.S. customary because no one uses it. It's the slug, by the way, but they don't even mention it here. Kilogram is the measure of mass in the SI unit. Now, in the metric unit, you might say it's just gram, but kilogram for the SI unit. Okay, which is the one everything else is based on. Ooh, that's all they give for weight and mass. And they don't even give us much room to work. There is an example here, two examples in fact, so we'll write it on this slide, even though the formula is right here. What is the weight? So we're looking for weight, that's the unknown here, of a 60.0 kilogram person. 60.0 kilograms, what's that a measure of? That's your mass measure, okay? On the surface of the earth, okay? They don't give us anything else. Can we do this?
Yes.
What is weight? Mass times the acceleration due to gravity, which we do know is a constant anywhere on the surface of the earth. So that would be 60.0 kilogram multiplied by 9.8 meters per second squared. Okay? And what would that be? 588 what? There is a 2 up there, you can't see it. It's what? Newtons, exactly. Or kilogram meter per second squared, either one of those. Okay? Wow, that's a lot of weight, isn't it? No, it's just a different unit. Now that's 60 kilogram person would be something about 132 pounds. So a pound is a much larger unit than a newton is. Okay? They measure the same thing, forces, but their scale is very, very different. Okay. Literally, if you're weighing yourself, I do every Monday morning that I remember to do it, then if that was a Newton scale, I'd really be worried because that'd be a huge, 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 huge number. Bad enough in pounds. Okay. All right. They got 5. Oh, notice what they did though? Even though this was 3 significant digits, our acceleration due to gravity is only 2. So they round this. You count 2 digits. That's 5, 8. But you look to the right, and the 8 moves that up to a 9, 59 newtons. But what they put was, oh, I'm sorry, I left off the 0. Okay, sorry. I got so carried away with what I thought they had. 590 newtons. Okay. Now, it doesn't really seem fair, but it is, because you only have 2 significant digits there. So, about 590 newtons. All right. Okay. Now, 211. A 60 kilogram person. They must be onto this. That is what? A measure of mass. Okay. Weighs 100 newtons on the moon. 100.0 in fact. Okay. The question is, what is the acceleration of gravity on the moon? So what we're looking for there is G sub m. This is G sub e. 9.8 meters per second. We don't usually write the sub E, but in this problem we ought to because the part of it was acceleration due to gravity. This is not 9.8 on the moon for several reasons. One, the moon is much less massive than the Earth, and number two, it's not as dense as the Earth, and number three, it's a much smaller radius, so there are lots of things working against it. So what would acceleration due to gravity be on the moon? That's your unknown here. What would be its formula? Second? Second? All right, yeah, you're giving me the answer, but what's the formula for it?
100 newtons equals 60 kilograms times.
Okay, say that a little louder.
It's 100 newtons equals 60 kilograms times.
Oh, I see. Okay. What you did here is the force. What you, going back to the force, well,
100 kilogram times.
yeah, okay. Okay. I'm going to call it weight. Weight on the moon is equal to the mass, which doesn't change, by the way, times the acceleration due to gravity on the moon. And that's what we're looking for. So the weight is what they say.
100.
Yeah, there it is. I knew it was somewhere. 100.0 newtons, which I'm going to write as kilogram meter per second squared. Times G on the moon. That's what we're looking for. Oh, I'm sorry. Is yeah, I know. Got ahead of myself there. Okay. I just don't have enough room. So the weight is this. I'm going to move the other side, which is rather bizarre, over here, and that's mg. The mass was 60.0 kilogram, and then the G for the moon is there. Okay, that's what we're looking for. So like you say, let's divide both sides by 60 kilograms. Okay, the kilograms go out and you're left with 1,000 divided by, 100 divided by 60, which you can really simplify by making 10 divided by 6, which is 1.66, I think it is. Okay. But they, second? 1.67, okay. 1.67, and the units will be meters per second squared. So that's the acceleration of gravity on the moon. Whoa, it's a lot less than ours. Ours is 9.8. So if someone will take 9.8 and divide it by 1.67 and see what the approximate ratio is.
5.868.
Yeah, pretty close to 6. Okay, pretty close to 6 times the gravitational acceleration of the Earth is what you get on the moon. Most of that is because the moon is much less massive than the Earth, but the other things like the diameters and things like that also matter. Okay, so that 1.67 meters per second squared, that's what they got to. It's sort of bizarre here. In the previous one, because we only knew this in 2 digits, they could only give a 2-digit answer here. But in this one, since they gave 3 digits here, 4 digits there, you can come up with an answer that's 3 digits. More precise answer on the moon than what they gave us for the Earth. But we were stuck with what they gave you, so that's what we live with. All right. So let's move to Newton's third law. How are we doing on time? Got a little over a half hour left, right? Okay. Newton's third law. This is a little different from the first two. The first law said an object maintains its state of motion or its state of rest, whichever it is, unless it's acted on by an unbalanced force. So it has constant velocity, straight line motion, horizontal motion, unless acted on by an unbalanced force, or it stays at rest unless acted on by an unbalanced force. The second law says, well, if you do have an unbalanced force, a net force, then you're going to give it an acceleration, which means a change of velocity. Okay. Both of those are talking about an object. An object, okay? Whatever that is. Newton's third law is a little different because the source of the force is other objects, okay? Now, it relates the forces between objects, but you have two objects involved. Here's how I understand that Newton described it. He said, if I push on a rock, I don't have a rock here, but I'm pushing on the desk. I'm really pushing on it. I'm not doing much to it. But notice there, it left a dent in my finger. That means the desk is pushing back on me too, okay? And that's basically Newton's third law. Third law relates forces between objects. Whenever two objects interact, whatever their interaction is, the force exerted on one object is equal in size, but opposite in direction. I pushed on the desk that way, it pushed back on me in the opposite direction. Same force exerted on the other object. Okay? And they're going to come up with an example of this later, and I'll give you one of my own. I'll give several later, but let's move on with this one, I guess. Okay? Whoa, they don't give much of one here. Here is the formula they give for it. I thought they would, but they don't. There's the force. The force on A due to B. The force acting on A due to B has to equal in magnitude the force of B on A, due to A. Okay? Equal in magnitude, but opposite in direction. So it doesn't matter which side you put the minus sign on. They have to be opposite in direction, but equal in magnitude. Okay? But always talking about two different forces. Okay. Oh, they do give some examples. I flipped over too far. Okay. Now, I have a pretty interesting little caption for the picture there, too. It was a football player, not quite the same as that one, but similar. Let's do example 212. I don't have a lot of space to write. So let's go back here and we'll write on this one. No. Hit the wrong button. Okay, there we go. Whew. Goodness, I'm running out of energy. I didn't have time but for a salad today. Goodness gracious. Calories are saying, where are you? I need some more. Not that I need any, but they think I do. Okay. Example 212. A 60-kilogram astronaut. Now this picture we're going to see later, okay? But we're going to do it now. 60-kilogram astronaut is freely floating in space, okay? Now, what does that imply to you? Should tell you two things right off the top. Freely floating in space. What does the floating part mean? There is no acceleration due to gravity. Freely floating in space. So he's outside, effectively, the gravitational field of the Earth. Okay? Most of our astronauts really aren't that, but they feel like they're that. Okay? So that's one thing. And he's in space. What's the other ramification of that? There is no air resistance. Okay, so here we've gotten a perfect picture here. No acceleration due to gravity, so there's no net forces acting on him, and there's no air resistance that he's having to overcome. So, he's freely floating in space. Oh, and what's this a measure of? 60 kilograms. They love that number, don't they? 60.0 kilograms. What's that a measure of? Mass of the astronaut. Okay? Freely floating in space and pushes on a freely floating 120 kilogram spacecraft. So we have a 120.0 kilogram spacecraft. What's that a measure of? Mass of the spacecraft. Okay? And he pushes on it with a force of 30 newtons. So his force, and this is on the spacecraft due to the astronaut. Okay? And this was 30.0 newtons. Okay, that's the force. And it says for 1.5 seconds. So what's that a measure of? That's the measure of your time interval, right? Over which he pushes. Just a... I'm so sorry.
What we measure?
I'm sorry?
We measure this. What we measure?
I can't hear you.
So what are we measuring for the
Oh, that's the delta T, sorry, it's pretty ugly. Time interval.
Oh, time.
Seconds, yeah.
I couldn't see it.
Yeah. Seconds are measure time. I like to put a delta T, meaning that's the time interval over which he was measuring. See if I can clean that up a little bit. I wrote kind of small because I didn't want to get into the other thing. Okay, that's what they gave us. The question says, A, compute or compare the forces exerted on the astronaut and on the spacecraft. So we know that the force of the astronaut on the spacecraft, the force on the spacecraft due to the astronaut is 30.0 newtons. They said compare that with the force exerted on the astronaut by the spacecraft. What would that be? So what we're looking for is the force by on the astronaut due to the spacecraft. What would that be? That would be minus 30. You're absolutely right. Newton's also 30.0 Newton, same precision. Okay? Because Newton's third law says that the force exerted on one object by the other is the same but opposite as the force exerted by the second object on the first. Okay? So that's actually the A down there. I put it up at the top. Okay? The B part says compute the acceleration of the astronaut or compare the acceleration of the astronaut to the acceleration of the spacecraft. So this was, A was minus 30.0 newtons. The B is what are the accelerations? Okay? Now, Newton's third law is relating to different objects, different forces, different things, okay? Different directions, okay? But the acceleration is the acceleration of one object due to one force, okay? So, what would be the acceleration of the astronaut. So this is acceleration of the astronaut. What would that be? What formula do you get that from? What relates to acceleration?
F divided by M.
Say again?
F divided by M.
Ah, very good. It's your net force on the astronaut divided by the mass of the astronaut. They're all on the same body. Okay? What's the net force on the astronaut? 30. Now, you could say minus 30. The book, I don't think, does that. Now, I'm going to change the newtons to the fundamental units, which are kilogram, meters per second squared. Okay? Divide that by the mass of the astronaut, which was 60 kilograms. And the kilograms go out, and that leaves you 0.500, I guess, meters per second squared. So it makes the astronaut's acceleration half a meter per second squared. If we put the sign in there, minus, which would probably be to the left, we assume. Okay? They don't put it in there. Okay? But it says compare that to the acceleration of the spacecraft, which would be what? Force of the spacecraft divided by the mass of the spacecraft. Well, force on the spacecraft was the same. It was 30.0, and don't use the newtons, but the fundamental units. What are they? Bless you. Kilogram, meter per second squared. Okay? Divided by, what's the mass of the spacecraft? What's the mass of the spacecraft? What's wrong? Oh. A flying bug or a crawling bug or what kind of bug? Is there something I can smash? Oh. You know what I call it? Stink bug.
Ooh, that's gonna be stank. You gonna make some more come.
Huh?
You gonna make some more come. Like when you smash it, you gonna make some more bugs come.
Really?
Yes.
Only if she's full of eggs, but.
It's the seed.
That is something I can stand.
Unless you're talking about the ants that are going to come to eat them, but that might cause more. Okay. Okay, what was the mass of the spacecraft? Back to where we were, huh? 120.0 kilograms, and again the kilograms go out, and what do you have? 30 divided by 120. 0.250 meters per second squared. So, even though the forces are equal and opposite, the accelerations are not, because the acceleration of the astronaut is greater, double that of the spacecraft. Why? Because the spacecraft is twice the mass of the astronaut. So, of course, their accelerations will be different too. Forces are equal, but opposite. The accelerations will not be equal. Still be in opposite directions. They don't use the signs here, but you really should. Okay. So we got that. There's also example 213. Normally I would erase, especially if I forgot, but I remembered this time. This depends on the previous problem, so we need to do it. After the interaction and acceleration between the astronaut and spacecraft described in 212, they both move away from their original positions. what is the new speed of each? Because they were both initially at rest, but now they're both accelerating, so what's the speed of each? So let's call V sub A, velocity of the spacecraft. What would that be? Now here we have to pull into play our time interval. How is velocity related to?
I thought it was constant.
I'm sorry?
I said I thought it was constant.
What is constant? The speed, okay. The forces are equal and opposite, okay? The accelerations we just saw are not equal and opposite,
Oh, okay.
okay? So if the accelerations aren't, the odds are the speeds aren't either,
Okay.
okay? Forces are equal and opposite, but the accelerations are not because they have different masses.
Okay.
So, what would be velocity of the astronaut? What formula relates velocity, acceleration, and time? Do you remember that one? Yes.
D-O-T?
Second?
D-O-T?
Is equal to acceleration? Is that what you're saying? That would be correct. But, yeah, V over T would equal acceleration. That is correct. Okay? Delta T. But we're looking for velocity, so that would be, isolate this by multiplying both sides by T. So its velocity is equal to acceleration times time. The acceleration of the astronaut was 0.500 meters per second squared times your time interval of 1.50 seconds. Now this second is going to cancel one of those out, but not both of them, and you're left with an acceleration, second?
0.75.
Okay, 0.750 meters per second, because you're left with meters per second. So that's the velocity of the astronaut. What's the velocity of the spacecraft? Goodness gracious. Oh yeah, I know what that is, okay. Velocity of the spacecraft is then, this is acceleration of the astronaut and the time interval. This will be acceleration of the spacecraft times the time interval. And what was the acceleration of the spacecraft? 0.250 meters per second squared. And multiply that by your 1.50 second. And it's what?
0.375.
0.375, and that would be meters per second. Okay? And you see that's exactly half of the velocity of the astronaut. And that makes sense too. Okay. And that's what they got in the book, I think. Yes. Yes, it is. 0.75 for the astronaut and spacecraft 0.375. Perfect. Okay. Any questions on Newton's 3 laws of motion? All right. How are we doing on time? We got about 10 to 15 minutes, right? So let's move on to momentum. And this will be another part of Thursday's lab. And this is basically, now we're getting into applications of forces and things, motion stuff. Momentum. It's an important property closely related to Newton's second law. I would say also the third law. Okay? We'll see that. Okay? Here is it includes the effects both of motion, which is your velocity, and inertia, which is your mass. Remember, inertia relates to mass, motion is measured by velocity. And this is it. Momentum. Now, where did they get the symbol P? I'm not sure. My guess, since Newton wrote in Latin, since back then all official scientific and educated people dealt in the Latin language, which was obsolete at the time, but they still did it because it was the official language of the Roman Empire. You know, they continued that even though this was millennia after the fall of the Roman Empire. Okay, not quite close. Certainly centuries. Okay, My guess is that the symbol he used for it in the Latin was something that translates to our P. It certainly has nothing to do with momentum that I can tell. But it's sort of handy because we have so many things that have M in it, it's good to use something else. So momentum is equal to mass times velocity. Now mass, remember, was a scalar quantity, just a number, no direction involved. But velocity always involves a motion. So that's a vector quantity. Momentum is also a vector quantity. So direction matters. When you do adding or subtracting, you have to do it vector addition or subtraction. Okay. So momentum is mass times velocity. Okay. Here's the picture that went with the last one. Remember the 60 kilogram astronaut, 0.75 meters per second in that direction. The 120 kilogram spacecraft, that's a pretty small looking spacecraft, would be twice as massive, but maybe it is. And its velocity was 0.375 meters per second in that direction. The momentum, now, the momentum before the astronaut pushed was what? If the astronaut was not moving and the spacecraft not moving, so velocities were zero, what was the momentum? Zero. Okay. So the momentum of the system was zero before he pushed, or she pushed. I can't tell which it is. Okay? So after the push, and then they picked up velocities and started moving in an opposite direction, the momentum of the astronaut was 60 kilograms, there's his mass, times velocity 0.75, zero, you can add those in. And when you multiply those together, you get 45 kilogram meters per second. Okay, what unit do we name for momentum? Actually, we don't. There is no unit for momentum. And this is sort of a shame, because frankly, if I understand, now I don't read Latin, so I've never read Newton's Principia. I'd probably find it fairly boring if I even read a translation of it. But from my understanding, Newton really didn't talk that much about forces. Now maybe he did, but he talked about this thing he called the quantity of motion. And what he defined as the quantity of motion was the mass times the velocity. So I think he was always talking about momentum, or not always, mostly talking about momentum. But when we do it in physics, we have forces, mass times acceleration. That's the big deal. We don't give nearly as much attention to momentum, which is his. So in my mind, they should have named the momentum after Newton, not the force. Okay, but they didn't. They named forces Newton's, not momentum. So we just call it kilogram meter per second. That's all, folks. We don't have a shortened name for it. Kilogram meter per second. Now, a little bit later, we're going to introduce another concept called an impulse, which is a change of momentum, and we'll give it a slightly different unit. It's still not going to be a name, but it'll have a slightly different weight. It means the same thing. Okay, spacecraft, on the other hand, 120 kilograms of mass, 0.375 meters per second is velocity. Multiply those two together, and guess what you get? 45 kilogram meter per second. Now what they left off here is the astronauts moving that way and the spacecraft moving that way. Astronaut minus 45 kilogram meters per second, spacecraft positive 45. So what's the total momentum of the system after the push? Zero. Plus minus equals zero. Okay, same values. Okay. So sure enough, the initial momentum of the system was zero. The final momentum, we'll learn later, had to be zero. Okay? That's the same example we were just using. I said the picture was going to come up later. There it is. They already had the answers on the picture, so I couldn't show it to you. Okay. Now, ooh. Okay. I thought there were some examples first. They're not. Now we're going to talk about conservation momentum. I basically just gave it to you before. The total momentum of a system before the collision or the push or whatever is the same as the total momentum after the collision or push or whatever. It has to be. Momentum is conserved. Just like mass is usually conserved. Only time it's not is in nuclear reactions. We're not going to have any of those, I hope, okay? So it'll be conserved. Even the firing of a rifle bullet, the momentum is conserved, okay? Now, have you ever fired a rifle? Okay. How do you do it? Okay. You hold the rifle up here and pull the trigger. Oh, you better hold it against the shoulder. Why not?
It's gonna kick back.
It's going to kick back. That's the principle of conservation of momentum. Because the same momentum that bullet has going out of the barrel, the rifle has the same momentum in the opposite direction, which is against your shoulder. So if you don't hold it against your shoulder, you got a big bruise, okay? Or maybe even a separated shoulder. That has happened before, okay? So you hold the rifle against your shoulder, and what happens now? You're part of the system. So you've just increased the mass from the mass of the rifle to the mass of the rifle plus your mass. So now the same momentum, but your mass is much bigger than the velocity is much smaller. So by holding it tightly against your shoulder, you can eliminate some pain. Okay. And here's what it says. Without your shoulder involved, the mass of the bullet, which is pretty small, yeah, but the velocity of the bullet is very, very large. So the product of those two is the momentum of the bullet in that direction that's equal exactly the opposite direction to the momentum of the rifle. Now the rifle is much more massive, but still it can have a pretty significant velocity against your shoulder, okay, if you don't hold it tightly against it. So the total momentum of a group of interacting objects remains the same in the absence of external forces. As long as you don't have any external forces here, basically with a rifle bullet, you know, the only force you have is the combustion in the bullet, but that's all internal to the system. Okay. Now, I sort of needed to go back. I promise you, I know you were looking forward to it. Another example, especially with the football players, and you know, conservation momentum or Newton's third law, that kind of stuff, they all tie together. I can remember either it was freshman or sophomore year in high school, I was on the second string on the football team. We had a very small high school, so you didn't have to be very big or very good or very fast or very anything, because I made the team. But anyway, it's not that funny. Okay. Yeah, he thinks it is. Okay. So, I was playing defensive end, which was one of my favorite positions ever. And we were playing against the first string offense, and the play came. We didn't know what play it was, but it came at us, and here came a really good pulling guard. And he was small, short, but very compact. And I don't know how I did it, but I imagined to avoid his block. Okay? Just in time to look up and see Bill Boyce. He was our next door neighbor. They owned the dairy right up the road from our farm. And so next door neighbors were pretty far apart, but still I knew Bill. Bill, being a dairyman, he drank milk for his water. I mean, he was heavy. He was not overly heavy, muscle heavy, okay? He was at least 190 pounds at the time, and I was probably at best 170 pounds at the time, okay? And here came Bill at full speed, just as I had avoided the block by Alvin, I can't think of his last name now, just missed him, just in time for me to, all I had time to do was open my arms and try to, well, I felt the knees just pumping against my body as Bill continued going down the field with me wrapped around him. But in time he did go down, but it was several yards down the field. But he had, his momentum was this way, mine was zero. At the end we had the same momentum total. I was just being dragged along with him. So that was my memory and how I think of conservation momentum. It's a bit on the painful side. Okay. Applications of this are collisions. Now, I don't know if you've ever been in a collision on the highway. Hopefully you haven't, but it was literally, it was when I first went to college. I think we had orientation for the week before school was begin. And seems like the Friday night or Saturday night before classes were to begin on Monday. My brother had gotten to town. He was 2 years older than me, but we both went to Georgia Tech. And he had a friend who had a car. We didn't have a car, and we couldn't afford one. My parents couldn't afford one. But Frank Michelle had a car. He had a nice car. It was a Z28. I don't know if y'all remember what that was. Nice little car. And they decided, and y'all probably won't remember the movie, Easy Rider had just come out. No one remembers Easy Rider, do you? It was a classic movie of its time. Y'all wouldn't even recognize the people if I named them, but sorry, I can't remember. Warren Beatty was the main character, pretty famous actor. Now no one's ever heard of him, but his sister was Shirley MacLaine. You may have heard of her, but she's old too. Okay, and the other guy, can't remember his name, but really this movie made him, and he became a really good actor after that. But he was good in this movie too. So we went to see Easy Rider. It was playing at the Capri Theater somewhere in Atlanta there. And Frank was driving, and Frank was a fast driver. Okay, but Frank didn't know where the Capri was, and Mike just my older brother, had a general idea, so he was trying to direct them, and but Frank was doing everything fast. I was in the back seat. They were in the front seat. I was in the back seat, so we're on set. And then Mike said, "There it is." Okay, it was across the street from where we were heading. So Frank turned right in front of an oncoming car that hit just behind the rear wheel, which is just where I was sitting, just in front of the rear wheel. So this was my welcome to Atlanta and going to college, first before classes ever began. So we didn't get to see Easy Rider that night, okay, because we were there with the police. What the police did, they got out the measuring tape and measured the skid marks of the other car, because that was one way they could determine its velocity, and ours, we were basically at rest. They were going to do that. Now, of course, it hit us before it finished its skid, so they were underestimating its velocity, but you see, everything went by conservation momentum. Did the police think, oh, this is a conservation momentum problem? Probably not. They had tables that worked this out for them, because everything follows the conservation momentum. Any kind of analyzing action-reaction interactions. That's a lot of action there, isn't it? Okay, here's another example. Have you ever played pool or billiards? Yay or nay? Yeah, okay. How do you start the game? Okay, you have the rack, okay, of the 10 balls. I believe it's
More than that.
yeah, way more. Yeah, what is it? 17 balls. Rack of 17 balls, right? Because you got 7. No, it's 15, isn't it? 7 above the 8 ball and 7 below the 8 ball. So the 8 ball, that would make it 15. Rack of 15 balls. Okay, and it's 1, 2, 3, 4, 5. I think that adds up to 15. Something like that. Okay. Anyway, so you have the rack of the balls there, and you have one cue ball, right? And you hit the cue ball at a pretty good rate. So the initial momentum of that system is the momentum of the cue ball, because all those in the rack are at rest. Zero momentum, right? Say again? So you hit it, and the initial momentum is all in the cue ball. The mass of the cue ball times the velocity of the cue ball, right? Now, when it hits the rack of balls, they go everywhere, don't they? They go bouncing everywhere. But guess what? The total momentum of all the balls bouncing all over the table there is still equal to the momentum of the cue ball. The difference is, cue ball's going in one dimension, this way. When it hits, for every ball that goes this way, there's another one going that way. If anything backs up this way, something else moves that way. So is it time in the middle of my story? That's how much you're enjoying my story.
No, I'm sorry.
Yeah, I see. Okay, got it. I know that. A little minus in the book, right by his name. Okay. All right. So that's another way to think of momentum. Okay.
You can finish your story. I'm just gonna let you know.
You wouldn't? No? Okay. It just goes on and on. Is that what you're trying to say? Oh, I see. Okay, I got it. All right, we'll pick up next time with example 214, which is dealing with conservation momentum. Okay. So, why don't y'all take you a little break? I'm going to have to shut things down here and go set up the lab. And we're in the lab that we've been in, 252. Say again?
Can we keep our stuff here? Come back.
Yeah, we'll be coming back so you can keep it there. You'll need pencil
The calculator.
and calculators for sure, but more the calculators here, but yeah, you might need them there too, so take the calculator.
Or sheet now, or you want?
Oh yeah, let me give you your sheets and pillowcases. I mean, no, just the sheets, okay. All right. Oh yeah, y'all are already awake now, you don't need the pillowcases.
Nope.
Okay. Wait a minute.
That's a Georgia
That's-
stick watch.
Yeah, it is. My wife gave it to me for Christmas a couple of Christmases ago.
It's like a customized watch.
Well, Georgia Tech is a lot of graduates there. So. But I have I need a pen. Okay, so.
Thank you.
Thanks for taking the load off my hands.
Yes, sir. You're welcome.
That was very kind.
Yeah, this is nice right here. My wife loves me because I was like, that's nice.
Well, somebody has to. Okay. You get one. Oh my. All right, talking about the lab number 3, this would be, right? I believe so, yeah. We're dealing on projectile motion, which is the same thing the text was calling compound motion, okay? We have 3 different types, horizontal motion. Part of this will be horizontal motion. I'll explain that to you in a bit. But then we will have vertical and horizontal motion. And vertical is the second type, and then the third type is compound motion, which they are calling projectile motion. It means the same thing. It has vertical component and horizontal component. Okay? Now, here's what we're assuming. You see the picture at the bottom of page 65 there. What you're going to be doing, we're going to take the meter stick, okay, and hold them up, put 0 at the bottom, that would be a good idea, and find where it's 10 centimeters from the tabletop, okay? That's going to be your initial drop point for the ball, release point for the ball. Metal balls are here on your track, okay? So you'll drop them from, or release them from there, let them roll down. What you're going to time with your stopwatches is the time it takes them to move the horizontal distance from here, right when it rolls off the table. So you're going to do this by ear, basically. You'll hear when it hits the tabletop, and you'll also hear when it goes off. So that's the time interval you're measuring. You're not measuring the time interval on the ramp. Not at all. Only the horizontal part. Okay? Basically, in your picture here, from B to C. Okay? Now, it says ignoring air resistance, there are no forces on the horizontal travel there. So all you're doing is measuring, and guess how far this track is? Set it up to be exactly. What is it, that hard to figure? 1 meter, exactly, which is how many centimeters?
90? Is it 100? 100?
I hope so. Okay, 100 centimeters. Okay, 100 centimeters. That's how long the horizontal portion is. That's what you're going to be timing, the horizontal portion of that. So you should know pretty close to what the horizontal component of the velocity is, because it's no net forces, so it should be constant speed all along there. You measure the distance divided by time. That's going to be your speed, right? Okay. Now, in the middle of page 66, we're going to get to a formula you're going to use later. Okay? And then on the, okay, here's your procedure. Let's jump to that. Okay? Now, one thing it says in the procedure you will not be doing. We're not going to adjust the ramp. What you're going to do is take the meter stick, and release the ball from 10 centimeters high, from 20 centimeters high, and from 30 centimeters high. So you use the same ramp, it's just where you're releasing the ball from. That's going to be, so you don't have the adjustment of that, which adjusts this, which is just, messes up everything. That's my modification of the thing here. Now, under number 2, measure and record delta y. You will do that. That's the distance that it falls from the tabletop to the floor. Okay, you'll measure that in centimeters. Okay? And then it says solve this equation on number 2. That's what we're going to do back in the classroom. So we will not get that far in here. Okay? We will do, we got to do it at least once. That's right. I'll talk you through it the first time, then we'll go to the classroom and do it. Okay? Because number 3, that's sort of the fun part. I put a cup at each place, and you're going to see how good your estimates are. Okay? And then there's some results that you'll do on the back page. But what you'll do from now is on table 6.1. Okay, does everybody understand?
Yes, sir.
Okay. Now, some things have been moved here, so let's make sure, maybe I'll move it very easy. Make sure you're 1 meter from the
We got to start now.
100 centimeters.
Oh. We got to start.
Yeah, no, don't drop it. Place it on there and release from rest. You sure that you want 10 centimeters off the top? Yes, okay, let's move these things out of the way so you have a clear path. Okay. Because we don't know if we can vibrate or not. Okay. Okay, you remember how to operate the stopwatches? The same button for start and stop. I think that's at what, 10 o'clock? Okay. And the one for reset is at 2 o'clock, and resets at 10 o'clock. Okay? So do your 10 centimeters. That's on table 6.1. Okay? Okay, now you do need to go on and do the calculations for the 10 centimeters. Yeah, we're going to do those. Because we have to do the cups.
We're going to do the calculations first, and then we'll
go. Here, and so it goes off here.
Well,
and you got 10 centimeters? 10 centimeters. No. Don't adjust that. Yeah. You do this, and find out where 10 centimeters is. I'll let you do it.
How far is it? What is it?
What is it? Don't do the track.
100 centimeters, 1 meter. No, 1 meter. We'll be on.
Okay. Have you done your calculations yet?
We're doing
Hold on this mic real quick.
What's that?
We got the whole table like. You right?
Okay. All three? 1.56, 1. Oh, wait. Oh, I mean, that's.
I know.
Okay.
Yeah.
centimeters track. 100 divided by.
So that A, the uppermost position around
This is divided by 2. Calculate.
He did that wrong. Dang, man. I don't know about this something out there.
Okay. Okay, we're only doing 10 centimeters, right? Yeah. Let's do the calculations for 10. I was wrong on that, so I'm going to have to do that. And then we'll come back and do 20 and 30. But for right now, do your calculations on 10. Yeah.
When it fall off the table and drop this, I start the timer, right?
I'm sorry?
I start the timer when it hits the table.
When it hits the table.
When it hits the floor.
Not when it hits the floor. When it rolls off the table.
It rolls off
The horizontal distance only.
Oh, wait, that's wrong.
Okay?
Okay, I got you.
Okay. Release from 10 centimeters then.
You ready?
Okay.
Alright, 1, 2, 3, go.
Wait. You don't stop it until it comes
It's all
up
good.
here.
It's easy.
Oh, okay. Okay, get the meter stick out of the way.
Yeah, you move it.
Okay. Come out.
It was
Okay.
22.
And you don't stop it. You, that's what
Yeah, I got it.
Right here?
Try one time. Wait.
Oh, so you clock it when it's off the table.
Yeah, that's what I was stopping at when you called it. That's why you didn't do it on the.
That looks a lot more right.
Yeah, okay. And then you take the average. Okay.
Just let me know how.
Did you do your vertical distance?
You can catch your still. I just.
Vertical distance, that's a.
Oh, there we go.
Floor to table side.
Alright, go ahead.
92.
Huh?
92 centimeters.
On the
You
nose.
gonna catch it?
92. You can't. You want to.
No, you gonna get it? Yeah, you get it. I'm telling you.
Like I said, I'm ready to paddle.
She said, full force, no warm up.
Wow.
I had to get that.
He got up, he said, please.
Y'all had 4, didn't you, before Bree came back here? Oh, okay, good.
Please, catch my
I was going to say, I lost it.
Oh,
Alright.
my goodness.
I'm on your attendance.
Man, did I even show
What's
you?
that?
Alright, bet. Attendance. You got me on my in on attendance.
Yeah, oh, I didn't. You're right. Thank you.
You check me off. Alright, bet.
I thought we might have lost you for good.
Alright.
I got you. Okay.
How do we figure out the last one?
Alright, y'all go.
Okay.
Come on now.
That's what we need a board for. So let me see if that board's available. I may write on it.
Hey, you can write right there, can't you?
Huh?
You can write on that, can't you?
What's the equation?
That plastic next time? That glass?
Okay. I don't have a marker for that, but let me see if there's.
Just get a sharpie.
Yeah, just a little more.
Alright, lost it.
Huh?
That's what the equation is.
I was asking about it. I don't know, Grace.
Lost
Hell,
it.
let's do this real quick. Let's go see if this one.
Are you okay? Oh, my bad.
40 centimeters.
Alright.
You ready to drop these down, Grace? You ready to drop these down?
Yeah.
Tommy.
Yeah, we'll chop.
I did find the board.
Bam.
Okay, Ken. Just like everybody else where you are. Okay. Now here's what we're going to have to do for that calculation, the calculator delta x. All right. Turn back a couple pages. All right. All right. Here's what we got. This is on page 66.
I was at the measurement.
Right after it says. On the right page. Yeah. Oh, no, it's on page 67. Okay, everybody pay attention?
Yes, sir.
On page 67.
Yes, sir.
Measure and record delta y, everybody did it, right?
Yes, sir.
Now here's the equation that they give you. Delta y is equal to 1/2 g. That sounds like my iPhone is getting torn up like that. Times divided by v sub x squared. Okay, join. Unfortunately, the last table over there. Okay. Sorry about that. That's what you get to come in late. Okay. Let me get Austin here. Okay. All right. You took my lap. Okay. All right. Okay. There's our basic equation. The one we're starting with. Everybody pay attention? Okay. Now, it says we know what delta y is. We just measured it. And the delta x is what we're going to calculate. It says solve this equation for delta x. Ooh. Okay, so what we're going to do is multiply both sides by 2 and vx squared. We know the vx, you just calculated it, right?
VX, that's the
You
time.
calculated the v, velocity. You did the 3 v's and you averaged. That's your v sub x, right?
Yes, sir.
Everybody got that?
No.
Okay, wait. All right. Okay, these are your times, right? These are seconds. Yeah. Seconds. So your velocity is, what was the length? 100 centimeters divided by that many seconds.
All right, I got a question.
Yes.
I'm still lost.
Okay, that's what we're talking about here.
Okay.
Here, that's your time. Okay. So what's your distance? 100 centimeters
Right.
divided by the time. That was your velocity.
All right, bitch. That's all I
Divided
need to
by
know.
time and velocity. So calculate those 3 velocities
All right.
for 10 centimeters, right?
Yes.
Okay. Calculate the 3 velocities for 10 centimeters and average them. Last time we threw out high and low. This time we actually do an average. Y'all average, right? Divided, yeah, added them together, divided by 3, right? Good deal. Okay. That gives you your v sub x.
Yes, sir.
Okay. Now, I'll let the other teams catch up there.
I thought you said we was a slow group.
Okay. Now, just want to tell Austin one thing. Probably on Thursday, I don't know for sure, will either be this lab, that lab, or one 259. I don't think we have to be in 259, but there is one lab coming up we do, but I don't think we do this Thursday. So look in all 3 places. And by the way, a couple of firsts. This is the first lab that the nice lab across the hall has been available. Okay, the other times have either been people studying there, people having a lab in there. Today was the first day nobody was there. But we needed to be here because we need the long tabletop. So we had to be here anyway. The other thing is every other time this board has been filled with stuff, today it's not, so we can't use it.
Whatever G is.
Add those 3, divided by 3. Right.
There you go. Hey, what's gravity?
What's gravity?
Yeah.
It's the thing that holds you down. Okay.
I'll say that again.
All right. What you mean?
What is G equal?
Oh, G. Okay, we're gonna get there. You're just ahead of me. Okay, hang on. Okay. So what we've got here, we're gonna solve. Kind of letting other people catch up. Everybody got your average v sub x.
Yes.
Okay. You put that on your table and take a look.
Yeah, we got it. What's the vertical? How do you find the vertical down?
The what?
The vertical is
Oh, okay.
you on it.
Meter stick.
Where do you get this one,
Meter stick. Come over here. Measure how far the ball's gonna drop.
I didn't buy it.
You want that video
I
again?
didn't buy it. That's why.
Okay. Get the meter stick over here. Measure the distance from the floor to the tabletop. That's going to be your delta y. Make sure you put the 0 at the bottom. Okay. Measure to the nearest 10th of a centimeter. Did y'all do that? Delta y? Okay.
Hold up. It wasn't on the ground. Huh?
Centimeter side, not the inch side. To the nearest 10th of a centimeter.
That's like 91.
I can't even agree to them like that.
91.8?
I would not agree.
91.8.
Okay, that's yours. It may be different from the other two. Okay. All right. So everybody has a delta Y now, right?
Yes, sir.
Everybody got it? Oh, you ask about G, we'll get there in a minute.
Please stop
So
hitting me.
you are going to calculate your delta X. Everybody got a V sub X, right?
Yes,
That's
sir.
the average of the three velocities, right? Okay. We need to solve this for delta X. Okay? So what we'll do is multiply both sides by 2 V sub X squared. Now we'll wipe them out, so this is 2 V sub X squared. That wipes out the 2 here, and the V sub X squared there. Okay? Now we need to divide by G. So divide both sides by G. That wipes out the G here. That gives us delta X squared is equal to, everything's gone but left, is equal to 2 V sub X squared times delta Y over G. Okay. We don't want delta X squared. We want delta X. How do we get delta X from there? Take a square root. So we'll take the square root of this and the square root of that. Okay? Now, so now we have delta X equal to, now, we can either leave everything under there or we can pull out the V sub X. Which would you rather do?
Take the V.
Take the VX out?
Yeah.
Okay, you can, but don't forget. Okay, so when you take out the square out of the square root, it just becomes V sub X.
It cancels.
No, it doesn't. It just comes outside.
Oh, okay.
Okay? And that'll be 2 delta Y over G. Now, Grayson asked a great question. Because, oh, he did? Okay. Okay, well, one second. I'm sorry. All right. What do we use for G? What do you think, maybe? What is G?
Gravity.
Yeah, acceleration due to gravity. Anyone know the measure of it?
98.8.
Not quite.
9.8.
9.8 meters per second squared. Right? Sound familiar? Except people, what was your V sub X measured in? Units are important. What was the V sub X measured in? Per second. And what was your delta Y measured in? Centimeters. That's in meters per second squared. So how many centimeters per second squared is that? Did I guess? 980. Because you moved it up in 2 places. 980 centimeters per second squared. That's what you use for G. Okay? Your question was what is gravity? His was what do we use for gravity, right?
A little bit both.
All right, well, a little bit. Okay. So when you're doing this calculation, be sure you use 980 centimeters per second squared. Okay? So, you've got your V sub X, fill it in, times the square root of 2 times your delta Y, you fill that in, and divide that by 980. But you only take the square root of this part, multiply it by your V sub X. What's that? This is the delta Y. I don't know what your value
Oh,
is.
yeah, I'm saying about square root.
The square root is over everything inside here. And then once you take the square root, multiply it by your V sub X, that gives you your delta X.
Would 1200 be like close, you reckon? Or is that way off?
That really sounds pretty high to me. Did you take a square root? Okay. Let me see your calculation.
I think it's like 98.1. No, 98.1.
Are you leaving the V sub X inside or outside? Okay. So you plugged in the numbers first, and now you're going to.
Yeah, I'm trying to work it out.
Yeah, and you're looking for the delta X squared here.
Yeah.
Okay. So what you're going to have to do distance multiplied by 2, multiplied by 65.3, is that what it is, squared? Well, that's a lot smaller number than I've been seeing in other tables. Okay. 1.56 seconds. Okay. That's what they're getting.
Oh, we got 1200, bro.
Huh?
Oh, we got 1200.
Yeah, but, okay. I'm just asking about that.
Oh, the time?
Yeah,
Oh, yes,
hi.
for sure.
That's the thing I'm asking
Yeah, I
about.
got the time.
Because, well, I've got to be, no, let me just see yours. See, the other groups are getting right around 1 second.
Yeah.
So you do your.
What y'all doing wrong?
What?
Y'all wasn't
Saw
small.
them rules on what?
Cause you know last.
Y'all watch out.
Last.
Saw them rules on where we catch these. That's 10,
Well,
right?
test or
10 right there.
Hey, all right.
Okay.
Alright, you ready?
Yeah.
So,
Wait. Where did you start to stop?
right there, as soon as I let it go.
Oh, yeah.
Table.
Man.
Off the table.
Right there. Table.
Man.
91.7.
Wait, you started right
You
away.
don't want me to.
Yeah, I did.
Oh, yeah.
Okay. It looked like you threw it up there somewhere.
So you really gonna do one?
No,
Yeah,
Yeah.
I'm ready from here.
I want
to
to
there.
say going out.
This is the table, so it all talks about.
I ain't trying to explain this.
Oh my goodness. All right, that sounds better. Okay, let's see what the calculation is. Okay, first, vertical distance delta y, that's not what you told me it was.
It's 91.7.
Okay, that's what you put there.
Oh. I thought you wanted us to do the square root thing. Plug that stuff in.
That's the delta x at the bottom. That's your bottom block. Delta x? Yeah. Delta x. You got 17 point.
43, 25, round it up.
Okay. And that should be centimeters. Is that what you got?
Yes.
Okay, what y'all get for your delta x?
I was rounding that up. It was 23.
That seems more reasonable. That should be in centimeters too. Okay, let me see your calculations on that. Okay.
I got multiply and then divide and then square root it and then
Okay,
multiply.
wait. Come here just a second. Vertical distance, that is distance. That's centimeters. Okay, centimeters. Okay, this is centimeters per second, right? Now, that can't be the average of those three, because it's way more than any one of them.
Talking about us now. What you did wrong?
Okay, you add that, divide by 3. Divide by 3. Yes.
Okay, so the vertical distance is going to be the same for all of them.
Yes,
right?
it is.
So can we go ahead and keep doing it?
Yeah, well, we got to do the cups first. I'm trying to get people at a place where they can do the cups.
Divide by.
Okay, and then we'll be ready to go. Has everybody got your delta x measurement? Okay?
Nope.
I know this team's still working on it. Some other team probably is taking 2 more measurements and working on it.
Oh, I'm tripping.
Just get all your measurements.
Oh, yes,
Right on, okay. All right. Yeah, that looks good now. Okay. And that's the number.
Okay, table out.
Let's go see it.
Yeah,
All right.
Hey, is this 114? Both of them? Like is the first one 114?
Yeah, the top one?
Yeah.
Yeah.
Alright, you know, I just
So,
Radical is 2.
what part is divided square root and then multiply by.
Let's,
Yeah.
Okay. Now, y'all got, does anyone move this?
I guess, I ain't got it. I don't know.
Okay. Are y'all ready to do your cut?
I mean, I don't know.
Sure.
Okay. What the delta X was your estimate about how far from this you were. What you need to do is line up the track and measure what the delta X you calculated right here from the base. Now you have to take into account that a little bit too. So measure whatever that was.
We'll take out 10.
Again, so you got this.
I thought it was going to be saved, but it's not.
Go and do the other ones.
All right.
Get the towel on? Yeah. Hey, catch these now. I think that was.
Okay, y'all done your delta X calculations?
Watch.
Anyway, have you done the delta X calculation?
So, can I get some?
Okay.
You want me to do the other ones?
Okay.
I got set up with the numbers plugged in. So go and put in a 9.8.
Yeah. 980 centimeters. Daily in centimeters, not in meters.
Okay.
Far easier to do it than try. Solve this for delta. Okay.
I got you.
Oh, that's lovely. That's in centimeters. But when you put that, let me see this again. See that again. This is your delta Y. The delta Y was this.
Oh.
We rang the cup.
Huh?
We rang the cup.
You rang the cup?
Yeah, but it fell over.
Okay, well, that's all right. Hey, way to go. You don't need to do the cup anymore.
Yeah, fuck I'm here.
Okay. Line this up for. Note that this is the time of year.
Vertical distance of the end, right?
Okay, what did y'all get?
46.
Second? Okay, wait. This is delta Y. This is from the floor to the thing. Yeah, well then put it there. Put delta Y there. That's what I'm going to be great. Put it down there. That sounds like a real centimeter. Wait. Did you put that where it needs to be? Good. What is your delta X calculation? What is your delta X calculation?
You did this.
17.94.
Looking good. Okay. And that's not per second, that's centimeters. Okay.
We still with someone else.
Hey, where did you put the cup?
Oh, the cup.
Okay, yeah, you put where the ball went and then you tried that cup. No, okay. That's not how we do it. Okay. Okay, let's do this part. Estimated this to be 46.6 centimeters. So measure that from the ground. On the ground. On the ground. That's delta X. Okay? No, on the centimeter side. Okay. Yeah, but not against the edge. Look at this. You got this width. Okay.
Graph 6.
Put the cup at 40, whatever you said it was.
66.
Okay. Now, make sure that's lined up with your hat there.
66, 60, and 60.
Does that look like it's lined up?
Used it.
Think it is? Hey, not from there.
From what? He told me anyway.
Oh, hey, I ain't that.
Hey, listen to him.
Wow.
That's the right place.
Yes.
Yep. You got it jammed up against the base. You didn't account for the lip. Okay.
All right.
Did you put it 40, whatever?
Yeah.
It
The
looked
other
like
side.
yeah.
That makes sense.
Yep. And you need again.
Centimeters.
Centimeters, very good.
Go ahead and do it again.
All right. Pretty close.
All right.
Pretty close. Okay. All right.
Pretty good.
All right, we're going to do it again.
Okay. Now it's up to you. You got close enough.
All right.
Okay. Now, go ahead and take that off the floor, and now go your 20 and your 30. 3 each, and do your calculations. Or you can just do the measurements, or we'll go back to the classroom and do the calculations.
All right, let's do it again.
Okay, how do y'all do on the second?
We're doing
What? Did y'all do your gut number?
Well,
Okay, what is delta X? Did you ever get it? All right. Okay. I worked it out. You see, delta X.
What about all you can't. I'm in it.
Delta X is equal to v sub x times square root of 2 delta y.
All right, come on.
Delta X equals v sub x.
How you doing? You doing 30. Just take it with
Square root of 2 delta y. Huh?
I'm sorry about that. What about it? You gonna go with it? You gonna read it out? All right. You ready? Go. You ready for the click off? The meter thing? All right, come on.
One full cut, one hit play.
Come on. Two.
Missing this shit.
Not exactly. 256.63.
This is what you're
Alright. Yeah, we get dirty right now.
When they finish
Yeah.
it,
Come on. Got it. Ball to it. Alright, you ready? You fair.
it's a water.
And all of them like literally 2 delta y and all this stuff. You use constant
Alright, good. Alright, you can move.
Shit, it's gas. This shit.
Come on, calculate this one.
Water.
Yeah,
It's not a lot. Yeah, it is. It may not be precise, but it's normal. Okay. So do the calculations and see what you come up with. Okay. You doing your delta y again? Are you doing delta y again?
You doing the same delta y? We're going to change.
Yeah, it's the same thing. Probably growing these.
Oh, no.
Okay.
Oh, so you, oh,
Okay.
That's what we're trying to do.
I was just letting you do his thing. I was like, you know, maybe me.
I thought I would change. That's what I was doing. Alright.
Let me just see how you set up here.
How you my boss even?
It's your first one? No. The last one.
Delta Y is 92. Over
It's on the
980.
test.
Multiply these two by 4.
I did those.
This is 2 times 92.
How you get from walkway?
CM divided by F. Centimeter divided by second.
Yeah, this is 184 divided by 92.
Centimeter divided by second.
Okay, well, how'd you get one?
You must be too late.
2 times 92.
Okay, did you ever multiply them? Okay, yeah. That's what I was waiting to say. Multiply that.
Right. You figure. Cover up. Look at about everything.
All right. Who was at my elbow? Huh?
How you divide 10 divided by 0.87 my boss?
Wait.
980 grams.
What are you trying to measure? Okay. All right. What is this supposed to be? This is your v sub x. That's the velocity in the x direction. Well, the velocity in the x direction is the distance from here to here, which is. No. The distance from here to here.
A meter.
Well, I had it set up this way. What is
Do
that?
you have that picture of the open?
It's like 100 today.
Okay, what is that? How many centimeters?
99.
No. That's a meter stick. How many centimeters in a meter?
1 foot? I don't know.
How many centimeters in a meter? 100! Centi! How many cents in a dollar? Okay.
Wait,
Is there-
what's that?
So it should be close. So I'm good.
Okay. Oh.
I got it.
Okay. Hey, we ran a couple.
What's that?
We ran a couple.
You weren't supposed to, but that's all right. Show off. Okay. So that shows that the time was probably okay. What did you get for your delta X?
50.2.
Second?
50.2.
Okay, that sounds reasonable. Centimeters. So now what you do is get your meter stick, as long as nothing's been moved too far here. Get the meter stick. Get the meter stick.
Oh, yes, sir.
Oh, okay. I thought that was hard to understand. Okay. Now, and how far was it?
How far was
What
that?
was it?
Oh, 92.
Was it? No, not there.
Is that on the floor?
Yeah.
From the end of the ramp.
What was your measure?
1 meter.
No, your calculation.
50.12.
Centimeters. Okay. On the floor. Right there. Except you have to count to this now. Okay.
So we count from here?
What's that?
And put one, count 50.1 centimeters.
My average.
Did you
You said
calculate this?
50.1, didn't you?
Did you calculate this?
Yeah.
You got them all points
A little bit over it.
seconds. Okay. Well, then I think I know what the average is.
Is that it?
138.9.
Okay, that's that. So I don't think they'll all be the same. Why don't you put it on the floor?
You
Just
said
estimate. No,
yes,
account for that.
Ain't the same.
Okay.
Yes, it might.
Okay.
There we go.
Okay. Then
Roll
put it on your 10
10
centimeter mark.
We hear it.
Huh?
Right.
Are you in line? Okay.
Also,
Oh, you undershot. So I think your calculation is probably overshot. I don't know why.
I started to kick the cup. I should have followed my first line. If I had kicked the cup, it would have made. I should have kicked
So
the
just don't hit the bucket. Okay. All right.
Nah, I ain't ready to kick the bucket.
But you came close. Okay. That's enough of that. You don't have to do the cups anymore. Okay.
Where's that?
Let's move on to the next one.
Man, you're all about throwing that thing at once.
Okay. Battery in my cup. I know. So y'all finished your lap? Okay. I've been recording all this, even though all the turmoil. Okay. All right. I know some teams are still working on taking measurements and calculations, but if you'll notice here, there's really nothing to do until you get, well, you've recorded everything on your data sheets, right? For all three heights, 10 centimeters, 20 centimeters, and 30 centimeters. Done the calculations on all three heights, okay? You came up with delta X's there. Okay, then on results on page 68, make a graph. All right, our favorite activity, right? And that's why all the teams have some meters, rulers here, so you can do it with your graph. And what you to do, with the velocity on the horizontal axis and the distance on the y-axis, the vertical axis. Now give me your range of your velocities, these are x's, the things you calculated. The bottom line, no, the top line here, the third,
Yeah.
103, 168, something like that. So that's the range of about 60.
Actually,
Okay. And how about your delta x's that you calculate?
You got 10 centimeters. How do you get that?
So that's about 30.
Centimeters.
So
10
we're going to put the
100.
piece of x's on the horizontal axis. I would definitely, so that's the larger range, right?
The velocity.
It's not what we like,
Yeah.
right?
Yes.
So do your graph.
Here, there's this question.
Do your velocity along here and your x delta x's up here.
Oh, yeah, you ain't got that.
Now,
Which one was it? 30?
what were your ranges from your piece of x? What was the week?
Very small.
Okay, so let's go with 100 here. Your rate was
168.
168. So 100, 110, 20, 30, 40, 60, 70. That's going to be pretty good that way. So 100 here, starting there. 110, 120, 130, 140, 150, 160.
Okay, and then the other ones, the range was 44.7 to 7.
Okay. So let's start 40 down here, 40, 50, 60, 70.
Okay.
Actually, we could do it, expand that. 40, 60, 80, 40, 50, 60, and I would,
So do 40, 50, 60, 70.
yeah, 40, 50, 60, 70. I don't want to go. Yeah, you're just a little too much to let down. Now, if you wanted to just to center it a little bit, you could actually put 30 down here. So 30, 40, 50, 60, 70. That could center it a little better, or you can keep all the, however you want. That will be fine the way you have it. And then plot the points. And use the straight edge for your best straight line, not these kinds of lines.
Do this on the graph on the back.
Okay. How are we doing?
Very good.
We got all three?
Do we do it on the graph on the back?
What's that?
Do we do that on this graph on the back?
Yeah, on the graph paper. Okay, and do it landscape mode, so your least of X's are that way, and your delta X's are this way. And I think, let me see your ranges of numbers, least of X's, which is smaller. What's that on? That's 20. I imagine it would be smaller than 10. Okay, so it's going from 115, right? Okay. To what's the highest?
2 north.
Okay, let's try it this way. Let's say, let's start with 100, 110, 20, 30, 40, 50, 110, 20, 30, 40, 50, 60, 70. You said 200?
290.
Whoa! Okay, let me try this again. 115 was your lowest, right? So let's do 110, 120, 130, 140, 150, 160, 170, 180. You go up to 290?
Well, that's what we're just doing from here to the second first image.
Okay. Okay, explain to me what you just asked.
Yeah, so it says 30 centimeters.
Right.
Around. We calculate it from here.
You measure the delta T, the time from, and you got those numbers. Can I just see one?
I'm trying to figure out what the next step
Oh, you want
is.
to?
What we're saying is like from here to the end of the table.
I just said,
That's what we're going to buy.
and, yeah, but, and I just want to see you do the time. Yeah, this what? 30.
30 up right here before. Put it up there.
Is that 30 right there?
Hold on, you want me to kick it
No,
out?
it's about
The other cup.
Let's do the meter stick.
See, another cup.
Okay, that's right.
30 up right there.
Really? Yeah, I thought I set it up for it to be at the end. Stop.
46.
That's a little more than what you have there. Good. 3 times.
Right again.
Okay.
I can't tell. I got a bad trigger finger, man.
Okay. All right. So what we do now, okay, so give me those 3.
Yeah, we're getting all about the same number.
You are?
Yes, sir.
Okay, well then use those. But you might have to double up down here then, but you have to make them fit.
Yes, sir.
That would be you just have to fix your scale so it all fit on there. Okay.
I'm on the ground. I don't know which one I can do.
Okay.
I did all the measurements for you.
Okay. Let me see your range of numbers. Okay. Your these of X's are going from 46, or let's just, okay. Let's just call it, let's just say 40. Just a low side, 40 to 70, let's say 40 to 80. Okay? Now that's your delta X. Okay, let's do the these of X first. These of X.
That's X. That's me. That's Y.
Okay. What it says here, right here, is the graph with the velocity on the horizontal axis and the distance on the vertical axis. Okay, so the velocities are going from 108, so let's call it 100, up to 170. Okay, so let's do 100, 100, 10, 20, 30, 40, 50, 60, 70. Okay.
Jeez.
No, 100, 110, 120, 130, 140, 150, 160, 170. It covers that range pretty well, right?
100, 120, 150.
No, 100, 110, 120.
Oh, yeah, sorry.
Wait, start 100. Okay. It doesn't matter.
I thought it was
Really.
0.
No. We're not starting at 0. Because we don't have room on the graph, and 0 doesn't really work here anyway.
Yeah.
Alright, and then what are your vertical scale? What's your delta x's? What do they run? 40, let's say 40 to 80. Okay, 40 to 80. So, we got plenty to work with. No, let's start here at, say, 30, 40, 50, 60, 70, 80. That uses the graph pretty well. Okay? Now, plot your points. Your horizontal scale would be your v sub x, and your vertical, your delta x. So that number on the horizontal, that on the vertical.
Okay. Like, I would say, want to pick one of these points and get it?
Well, it's something close to your that line. That's not far off. So you can see y from, and that's not far off either. So you're changing y from, drag you up here. So that way,
This is just a increasing line.
Draw a straight line.
Huh?
Increase line.
okay, and get your ruler and draw your best straight line through those 3 points. Just the ruler, however is necessary. Okay, so y'all get your scale worked out.
Oh, no, it doesn't.
Hey, that's not bad.
I come up here and
Yeah, let me get you some better ruler. Sorry.
Thank you.
I
want you to-
as close as possible to those 3 dots.
I don't want you to do it. I want you to help me with this ruler. Oh, I'm sorry.
Okay.
No.
What's that? 169 and 69.
It was, what? 100, so would it not be 169? Oh, 100.
Oh, no, 143, 100, yeah.
Alright, we got it. Alright.
Is this just telling us? Oh, this is just perceiving.
Straight line.
All right, good. Okay.
That's all it is. Yeah.
All right.
Alright, and then,
You calculate the slope, right?
rise over run.
Rise over run.
Okay.
These are right here.
Checking mine is 30.
That's the last point.
It's, so it's 30 over.
165.
Oh,
It's
look at
only
that.
6.
Look at that. Look at that.
It's 72.
Huh?
It's 72 over 165. Right. No. 165 is 72. It's last point. I know that right.
Okay, yeah. That is 72 on Y.
72 on Y. And X is 165.
Okay. But you're going to this one. So rise is the difference of this value and that value. Change that Y.
Do you do the highest?
Y value here minus the Y value. And then the change
You
value.
divide it.
Okay,
Well,
see,
not-
The
the
highest?
these are exactly the
And we made
same.
the graph.
The highest.
I don't-
It's 72.
72.
72.
0.
So
Huh?
that's exactly.
45.
Yeah, it's awfully close. Now, you didn't put units on this. What was your delta, what was your Y measure?
So don't write that right now. 45.
Scale? This was distance in what units? I mean, what units?
Centimeters.
Centimeters. Okay. And what's your, and what's your, that was Y.
Okay, not that.
What's your run measure? Okay. Your run. Run was centimeters per second. Yeah, 1 over 1 over section. Okay, now down here, your piece of Y is also in seconds.
Yeah.
So
Those per seconds.
yeah.
So percentage error is 0.
So, it says some point right here, and that point right here.
Right, the Y.
And why? And 1.6.
Okay, wait. The difference between this and that, difference is subtraction.
Subtraction. I can subtract this now.
Is it Y2 minus Y1?
Y2 minus Y1, exactly. Over X2 minus X1, exactly. So if you have those 2 points, and then you divide the delta Y divided by the delta X.
Then that's the slope.
That's your slope. Okay. Bless you.
Hey,
I mean.
I'm good.
Okay, what y'all get this?
Yeah, no, two
Oh, you
right.
still- yeah.
I'm trying to calculate what TY is. Calculate TY.
Okay, wait. Second here. Have you done this yet?
That's all right.
Yeah, no.
Do that first.
What's that?
Make your graph velocity. Oh, yeah, I did that, I think.
Where's your graph?
I just feel like it. Pretty precise.
Okay. So your change of Y, your slope of the change of Y. So whatever Y value that is, minus whatever Y value that is, that's Y. And then whatever X value is measuring the same point, whatever point you use.
You gotta divide that.
Your graph.
Yes, sir.
Okay.
Oh, from here.
Yeah, pick a point on your graph, and that's what you're measuring.
So I'm gonna measure from here to the beginning.
Yeah, and do your change of Y and the change of X.
1, 6. 60.
That's your change of Y.
Yes, sir.
Okay.
So that'd be centimeters. That'd be centimeters.
At the top, yeah, that'd be centimeters. 60 centimeters. If that's what it was. Okay, divided by change of X.
TY is the.
Okay. Calculate TY from the screw that you know what your delta Y is.
Yeah.
2 times X divided by G, the G is
980.
980. And that's your delta Y. And square root of that. That's the square root
Right.
of that.
So I got to do each. How do you do?
Yeah.
Y.
Delta Y didn't change, did it?
And then
What you
He
trying to figure out?
did, yeah. So take the square root of that.
What you trying to figure out? Yeah, that's it right there. Yeah. That's what I was figuring out.
What you get?
G 72 and G is 980. Yeah. It's still
Make sure everything's.
You
So
feel?
what's
You just square root of
I'm so excited you can keep it.
Good deal, thank you.
Also, here's that.
Oh.
And then, okay, look, here's my paper, my
Okay.
research paper, but my printer, like, moved my works cited page down some. It was not like that when I typed it, but, and then I have the page to one of the sources.
Excellent.
Okay,
So this how you do
there
it?
you go.
Okay. I need to put these boxes. Okay. Thank you.
The whole thing.
Hey, how do we figure out number 2?
Yeah.
2 so we get our number 1.
Okay. TY from the square root of 2 double y divided by 2.
I think I
Got it,
skipped
double
this
y.
one.
Yes, sir.
I tried to, I ain't doing
It should come up fairly close to this, but did you, let me see you do the 2 delta y, 2 delta y.
Craig, what was our delta Y?
now. English first.
On that? Oh, 92, okay. We do. Two.
Well, if we run major, though, we got to go in. I had some new plans like that.
Huh?
Get back.
How did you get a different?
I guess some more online. We don't know what we got for number.
I use the numbers, yeah. I subtracted the highest, number, like, by the way. So for I subtracted 293, 295.
I'll look at my
You got it.
Two times. 92 times 5.
Yeah. Do what?
What is that? 2?
This is right
You
here.
got one
This is around this way. So the difference here is.
take the square root of.
What is that?
Got the turn your phone sideways.
Yeah. Okay. The rise is from
You gotta worry about it.
45, 72, 945. That's
Yeah. And then you take the square root, which is
65 to 108. Exactly. On his
That's what it is calculated, not what I got from that graph.
I would check that on the graph.
That's just me there.
well, if you're looking at the graph, you can't really tell the exact number. I use the exact number.
Well, yeah, this one was 98, it's a lot more.
That's what I was getting wrong.
That's why I gave you square ruler.
Yeah, he's still
So
doing
you
it.
can do that's straight line you can. So yeah, if you want to go up a little bit. So if you did the calculation right,
That's what I did, was looking at the graph, and he calculated it.
Oh,
on the graph, you have this 120, no, 117.
That's because they use the angle. You turn it in online, they got some raise around there. They
I did 60 right there and I did 120 right there.
Okay. Okay. Yeah, this one is, if that's the feature, then it'll probably or something like that. You'll get a little better, it won't be exact, but it's a lot better. Okay, well then you just share it.
Alright. I did calculation, came out.
Really close, really close. So the difference here is what? 0.04?
Yes.
Okay. 0.04 divided by that.
Divided by,
You need to sit here.
so 0.4.
Yeah, divide that and multiply by 100, so 100%.
Read the story online.
Yes, I did.
So it's not far off.
And now we're going to
Is it 1.05?
Good 5%.
No, 0.05, that's it, divided by that.
0.05 divided by
0.4.
and then
Okay. Not 1.25%. Anything less than 15, you're pretty good. Okay.
It's been 11%.
That sounds reasonable. Anything? Oh, okay, yeah.
Oh, I'm about to say it.
Good deal.
Oh my God.
All right. Good deal.
You see, you got on this? This is how much stuff we get.
It was well worthwhile?
It was worthwhile, for sure.
All right, that's a good answer anyway. Okay.
You don't gotta do what you think you
Man, I failed this shit. Oh, they work online. I hated this. That teacher. I didn't know you could drop a class before you failed it. I would have did that, but I failed it. I failed though. Fuck out that class. I ain't even gonna take it. What you call it?
Did you feel like
But it's so much.
Yeah, at first I did.
Oh, yeah, so much.
After I just looked at the yeah, the history we covered last day.
What was the purpose of the lab?
Yeah. We started. We started compound motion, I think. So, no, we started over here.
Right.
Yeah. No, we started falling off. Yeah, we had covered that part last time. Okay. So we started 2.4, all the way to, and there were quite a few problems that we did to down. And we got down to, this is that's where we were starting at. Are there any more major questions before I need to turn off the board, turn off the recording? Okay.